Imagine a world in which assistive technologies seamlessly compensate for movement disabilities, allowing persons with disabilities to independently pursue their activities and fully participate in society. Imagine a world where these technologies are developed by and in close collaboration with users, and thus highly accepted. Over the next 2 days, we want to explore how close we currently are to this world, which challenges await us along the way, and which solutions may help us overcome these challenges. My name is Roger Gassert, and I warmly welcome you to the Cybathlon Symposium 2020, live from Zurich. I have the pleasure of hosting this symposium together with my colleague Olivier Lambercy, whom you will meet in a few minutes. This is a special time, and this is not how we had envisioned the Cybathlon Symposium 2020. We were looking forward to welcoming you in Zurich around great talks, posters, and of course, delicious Swiss food. However, with every challenge also come opportunities. And we are therefore extremely excited to welcome you to this virtual symposium. We are especially thrilled to do this as a first step into the new Cybathlon global format. Over the next 2 days, we will hear from a great lineup of junior and senior experts in the 6 disciplines of the Cybathlon, with 6 keynotes, 8 short talks, a panel discussion, as well as a poster session via Twitter and Zoom. 3 of our presenters will speak to us not only as researchers and developers, but also as users of assistive technology. We gratefully acknowledge the support of our symposium partner, the Stavros Niarchos Foundation, without whom this event would not have been possible, especially in its current form as a free event open to anyone interested. Before I now give the word to Olivier for his welcoming remarks, I'm pleased to now hand over to Professor Heini Murer to address his welcome words in the name of the Stavros Niarchos Foundation.
Dear friends, on behalf of the Board of Directors of the Stavros Niarchos Foundation, SNF, it's my pleasure and honor to welcome you to the 2020 Cybathlon Symposium. I would like to extend a special welcome to all of the students who are joining us today. This may not be the form in which we expected the symposium to take place, but this virtual format does have advantages. We are particularly excited that the organizers made a priority of welcoming anyone interested to participate free of charge. This furthers a core priority of both the Cybathlon and the SNF as an international grant-making organization, opening productive channels of access and collaboration between experts and the public. This new reality brought upon us by the pandemic, in which virtual events like this are the norm, results from a rapid paradigm shift. a new way of doing things suddenly became possible because it suddenly became necessary. It raises the question of what other fundamental transformations could be achieved if we perceive them as necessary, and calls us to question what we can learn from the opportunities and the drawbacks for accessibility our new virtual existing presents. Meanwhile, our situation is a reminder of how easy it is to be complacent in assuming that science, medicine, and technology will inevitably advance over time to address and eliminate the challenges facing society. On the contrary, these advances require international effort, thoughtful collaboration, and persistent focus, qualities embodied in the Cybertron's mission. Through thousands of grants in over 130 countries and around the world, SNF has focused both on supporting critical long-term efforts like the Cybertron's international goals and delivering immediate relief from pressing crises like those engendered by the pandemic. On behalf of the Foundation, thank you all for being here and best wishes for a productive 2 days.
Welcome as well from my side. My name is Olivier Lambercy, and I have the pleasure to co-host the Cybertron Symposium 2020. As Roger mentioned, we have a bit of a special format this year, so let me give you a few additional technical details. We are now live from Zurich, and we will have a mix of both live and pre-recorded talks. Depending from where you're watching us, the program might be a few minutes delayed due to the YouTube stream. However, since we are still streaming from Switzerland, we will do our best to closely stick to our schedule, which has been slightly updated, so please refer to our website for the latest version. During the entire event, we will provide live translation in International Sign Language, as well as a live closed captioning service. If you want to access it, please activate this option in the settings of your YouTube player. Each talk will be followed by a Q&A session, with our speaker joining us live. So if you have questions to our speakers, you can send them via email to symposium@cybertron.com or use the chat function in YouTube. For this purpose, follow the link on the YouTube channel and access the chat beside the video stream. Note that the chat is intended to ask questions, not to discuss with other participants. It will be set to slow mode and it will be moderated by us. At the end of each talk, we will bring your question to our speakers. Now some quick information as well regarding the poster session. An interactive booklet is already available on the landing page of our website, so you can read all accepted abstracts before the poster session. Today, poster will be tweeted on the Cybertron channel, and tomorrow, poster presenters will wait for you in dedicated Zoom meeting rooms for exciting interactive presentation and demos. The Zoom links will be posted together with poster titles on the landing page shortly before the poster session tomorrow. Don't hesitate to be active on social media, follow and comment the poster that will be uploaded on Twitter, and of course, share your opinion on the event. Final point, in case we should experience technical issues, please reload the landing page of our website to check for updates. All right, now that you know everything, we can start our scientific program and switch over to the first block of the symposium, which will be related to powered wheelchair. I wish you a very inspiring and stimulating Cybertron Symposium.
I'm excited to now introduce our first keynote speaker, Dr. Amit Gofer, joining us live from Israel. Amit, welcome to the Cybertron Symposium. Thank you for being with us.
I'm very happy to be with you and talk about the problems and troubles and probable robotic solutions of people that are confined to wheelchairs, or in general people that are can't walk and so.
It's really great to have you here, Amit. I will shortly introduce you, and then we will start with your talk.
Okay.
Amit is the inventor of the Rewalk Gait exoskeleton and the founder of Rewalk Robotics. He is also the founder of Up and Ride Robotics, a company that developed the Up and Ride, a robotic mobility device. Amit holds an MSc from Tel Aviv University and a PhD from Drexel University, both in electrical and computer engineering. As a wheelchair user, a technology developer, and a successful entrepreneur, Amit will give us a unique perspective on the benefits of upright rolling with a robotic wheelchair. Amit, we look forward to your talk.
Thank you. Just let me move my image. Sorry for that. Okay. Well, I'll start with the most important thing for a person that is paralyzed or limited in his abilities to stand or so, is the be at eye level with others. This is what I wish and others. And we do it here with Up and Ride, a self-balancing wheeled mobility device. The two pictures actually shows everything that I mean to introduce. At the left, you see me in the middle with my friends at Rehacare, this dog, about 5 years ago, before. And I'm able to stand with them and drink a cup of coffee and then lunch and be part of the group. And that was a tremendous feeling. On the right, there is a person. He is also quadriplegic like myself, and he is standing up and right and vertical, while the chair is on a sloped ramp. I'll continue. Okay. Oh, I see, doesn't work here. Just a second. Okay. So again, Up and Ride, and it's a robotic solution for the disabled community. And again, most important, regain the ability to be able to be in eye level. So the problem, as very nicely was phrased by Ruth Harrigan. She's an author of books, and one of the first things I noticed after I started using a wheelchair was what a great view I had of good-looking asses. Well, it is funny but sad, because this is true. In the elevator and when you have around you a crowd and so, your head is where it is. And the young lady on the right, nobody can see her because she's so little. And being an adult at the height of a child is humiliating experience. So confinement to wheelchair causes loss of self-esteem, which is one of, or maybe the main issue here. Limited mobility, health deterioration, exclusion. The disabled not always feel as part of the core of society. All this results in poor quality of life, of course, very high medical expenses and other related expenses.
Which item in this picture do you think negatively affects people's health more than anything else? Alcohol? Cigarettes? The donut? Hamburger? Sure, they're all pretty bad for you, but most people know that and at least try to limit their intake somewhat to these items, even a little bit. But it's the things we don't think about that can really cause damage. Things we use every day so regularly we don't even think about how its constant use could actually be killing us. The real culprit is the chair. We were given legs for a reason. Most third world cultures don't even have chairs, and they walk an average of 10 miles a day. We in the modern world, on the other hand, spend most of our entire waking days sitting down. People go right from bed to sitting on the toilet, after which they sit at the breakfast table, then they sit in a car as they drive to work and spend the entire day sitting at a desk, only getting up to sit in the toilet and in the cafeteria. Then they sit in the car to drive and sit at the local bar for happy hour. Then when they've had enough of that, they go drive home and spend the rest of the day sitting in a comfortable chair watching TV before they crawl to bed to recover from all the physical exertion that day. And when people go out, they sit at a restaurant or a movie theater. Sitting all day is far worse for you than you might think.
Well, more of the problems is hazards of sedentary behavior. It increases risk of severe medical disorders, including chronic urinary tract infection, which is actually the killer, number one among people like with spinal cord injury, for example. High level of cholesterol and triglycerides, accelerated formation of abnormal fat or lipid masses, and so on. Strokes and coronary heart disease and chronic pain. Other is the deterioration of general health and body condition, pressure ulcer. That you know when it starts, you never know it. It will take a month or half a year. Muscle atrophy, increase of total fat, obesity, osteoporosis, and degraded bowel and bladder function. And in my opinion, maybe the number one is a psychological deterioration due to loss of self-esteem, sense of exclusion, and damage to mind-body balance. So the disabled community, they crave for inclusion, part of society, quality of life, independence. As you can see on the left, a guy using the rewalk, climbing stairs, and the one on the right, no need any explanation, up and right mobility and health. Just think about how many years at the 20 centuries of a wheelchair that is the only solution. You have it at the 6th century on a Chinese engraving, and you have it today. Actually, nothing has much change regarding that, which is very sad. Now, look at down the picture. You can see me riding down the slope and then up the slope. This is the up and ride. Our goal is to develop the next generation of stand-up wheelchair, indoors and outdoors. The outdoors I highlighted here because no device today can take a paralyzed person outside standing. And I'll talk about it later a bit more. Now look at the Rewalk app. Rewalk I developed it before the Up and Ride. The idea was to fundamentally change the health and life experiences of a mobility impaired individual. So you can see here it takes a person that is typically confined to a wheelchair and enables him to stand, walk, including stairs, and so this is the one of these are the robotic solutions for the disabled that we have today. Okay, standing is an effective way of counterbalancing many of the negative effects of the constant sitting. On the left is upright. You see the person is vertical, while the wheelchair, the base is not, is tilted, is vertical. And on the right, you see this nice lady that uses the crutches to walk. She's paraplegic. Only people that can use crutches can use the Rewalk. And you see that both of them are really relaxed. They don't have to waste too much energy or strain. They can keep on hours with that. Now the Technion, I think, here will introduce the subject.
For centuries, technology has offered just one option to quadriplegics, persons paralyzed below the neck. This option was the wheelchair. Behind the innovation revolution for paraplegics and quadriplegics is Dr. Amit Goffer, a Technion graduate and entrepreneur. The Up and Ride brings quadriplegics from a sitting position to an upright position, both indoors and outdoors. Recharged overnight, it can negotiate a variety of surfaces, sidewalks, and slopes, responding automatically to obstacles and hazards.
Being able to stand and move is extremely important for people with psychological health, not only the physical one, and the dignity of the person, self-esteem.
After an accident left him quadriplegic, at first, Goffer put his ingenuity into developing the Rewalk, a revolutionary system that enables paraplegics to walk, climb stairs, and even participate in marathons.
When I started with the Rewalk robotics device, I was wondering how come wheelchairs are the only solution for people that are paralyzed. So this was like my great motivation that it will be kind of replacement to wheelchairs.
Just in the developed world, there are about 8 million wheelchair users. If you go to the rest of the world, it's about 70 million. Rewalk returns the functionality of walking, but not every wheelchair user can use the Rewalk. And the Up and Ride is the solution for all those people that cannot use the Rewalk. During the time that we were working on the Rewalk, we were always asked about Amit, can he use it? Can you use it? And we had to say no. Amit was injured in 1997. Just August last year, 2015, he was first time went out from his home in standing position.
The first time I used the device, it was the exhibition in Reha Care, Düsseldorf, Germany, and it was the Alpha, the first model. And it was it was a very strange feeling, and a good one, extremely good.
Goffer's passion is not just to create successful startups, but to improve quality of life for millions.
What I did in Rewalk Robotics and what I do now in Up and Ride is helping people that are disabled. The connection actually that I have with the people and their families is so moving, is so different from anything else. And the way that the families cry on my shoulder and say that I changed their lives, And so I think that no exit can compete that feeling.
Okay, we have in the market standing wheelchairs. I'm using one. So one reason that they can operate only indoors and outdoors they are not safe. The stability which measured by the center of gravity is different in the position of sitting and standing. So when you sit, it's okay and fine, but when you stand, there is the danger of flipping over. So you can't compensate with these devices on slopes. And you can see at the lady standing in other chairs that are at the bottom, you have small wheels, so to stabilize them. Waiting for the next slide. Okay, so many of the disabled are still practicing in our company, and then all kind of difference. On the top left, you see CP, cerebral palsy, and then SP, which is also a deteriorating disease of muscle, a ALS, traumatic brain injury, and quadriplegic like myself, the two on the left down, and of course paraplegic. This is more of the same. I think I'll skip it. Attributes of the device. The modes: sitting, standing, in between sitting and standing, bar sitting, which I'll show you how important it is, and reclining. Mobility at all these modes. And also mobility indoors and outdoors, as I said, and on slanted surfaces, slopes. Safety is a very important issue here. A user center of gravity, as I said, remains in place, and that gives maximum stability. How to balancing mechanism based on a gyro and more electronics ensures that the user is vertical and stable, and the stability thus is achieved on slopes. Automatic safety features also prevent hazardous situations. Oh, this is very important slide. Again, benefit quality of life. You have high-level view in social interactions, enhanced self-esteem, improves the device, improves overall health, and reduces the visibility of the disability. And it is very important because it is for all those illnesses and sickness and conditions of person that are not being solved by the ReWalk. Paraplegic are, of course, quadriplegic, multiple sclerosis, CP, TBI, and the elderly community and others. Now, pay attention to the photo on the left down. You can see me standing at the bar, but alas, I was too high, or if you want, the bar was too low. So what I did, I used the mode of the bar sitting. It is sitting but high, and that was very convenient and nice. And at the very right, you can maybe understand why being at eye level is important. I could talk with a person as everyone else. These are testimonials that were
a miracle. This machine is an absolute miracle. I would love to have one. Absolutely love. It would make a big difference in somebody's life, being able to stand up and not have to look at the world from down below. It's unbelievably stable. It drives smoothly, reacts very quickly, and it's a wonderful device. I'd love to have it.
Great. I enjoyed it, every minute of it, from the sitting position and the standing. I mean, it's a wonderful machine.
It's really comfortable on your knees too, which is surprising because most are not.
I liked that you're able to go fairly fast while still standing. It's nice to be able to stand up and drive around at the same time.
The stand-up wheelchair is the way to go. I mean, it gave you a sense of being actually upright and walking versus being down and looking at everybody's waistbands. Being upright to me is a great sensation. I didn't have any fears or qualms about going up and down the ramps. This thing counterbalances when you're driving up and down ramps. The gyroscope, I think, is an excellent invention on keeping your stabilization level and keeping your center of gravity up.
Wow.
It wasn't scary at all. It wasn't. They all talk about it. It wasn't scary.
This is awesome. I would purchase one of these. Even if I didn't need a wheelchair, I'd purchase one of these.
I hope that you enjoy. So I will join. There will be a competition. Thank you.
We seem to be experiencing technical problems. Please give us a short moment while we try to reconnect with Amit. Amit, can you hear me?
I can hear you. There are interruption in the middle.
We had a short interruption, yes. Maybe you can just pick up the last couple of sentences.
Going back. Okay, the really last ones. Okay.
Maybe the last slide. Can we put the last slide back up, please? Okay. This is just us, the group. You can see mixture of the middle and down and the low pictures. All our partners, all that we established in the company, and you can see also people using the up and right and the rewalk. And what I said that I hope that other companies will join in developing to the rewalk. Yes, every university in the world almost they have their own exoskeletons, which I must say they don't really function well, but this is the beginning. And the same would be very happy if, when a person got in the situation of spinal cord injury or illness or something, he will be offered as a first option, not the common wheelchair, but one of
those or up and ride or rewalk according to its condition, but not only the wheelchair. Now, if other companies will join in and there's the competition, and what I said, the last sentence, I think competition is good for us, for everyone.
Thank you so much, Amit, for these profound insights and also these touching testimonials in your presentation. I apologize for the technical issues we had, but I think the main messages came well across. Let me start.
Thank you.
Let me start with the first question to you, Amit. I was wondering, you first developed the exoskeleton and then the standing wheelchair. Why did you not do it the other way around?
Because I was very intrigued and curious about a robot that makes the person go, climb stairs, do everything. I wasn't, before that, the company that I founded was an MRI company. Nothing to do with people that are in the wheelchair. Only it was 1997 that I myself got into the situation. It took me 2 years to find my way around. And then, since it wasn't the first company that I founded, I knew how to do it. It was very, very, fantastic thing for me to do.
Okay, I noticed, I believe in one of the videos we saw where you mentioned that the exoskeletons would replace the wheelchair at some point. So I guess you were directly aiming for that target.
The exoskeleton, I'm not, this is the Rewalk. This company I left about 6 years. And I think that a good exoskeleton, the person doesn't need also a wheelchair, because when he walks and then gets tired, he or she, the person can just sit down. And why the wheelchair is not reasonable to continue using it. The up and ride is also a wheelchair.
Yes. Thank you, Amit. Let me now check if we have questions from the audience.
Thank you.
And the first one here would be, I would like to know what the main obstacles are for introducing this technology in stroke, spinal cord injury, ALS, just in rehabilitation in general and neurological injuries. What are the main challenges?
I'm talking about the up and ride. Well, to begin with, it was designed to fit anyone. Controlling the device, I mean, if I go back to the exoskeleton, to the Rewalk, you have to learn, like learning how to drive. For someone, it can take 4 days. Other guy can take 4 weeks, or she or him. And here, in the up and right, you use the regular driving control that you have on almost every electric wheelchair. And if you can't use the hands, then you can use a system that we already have integrated it, but only for our experiment, that you can, enough for you to use the head and the eyes, click with the eyes to make it go. So even a person, and we tried it on people that they hardly can do anything with their body. Does it answer the question?
I think that it answers from the side of the wheelchairs, and maybe you can also say a few words about challenges for introducing exoskeletons. I know that more and more clinics are now integrating exoskeletons for the initial therapy, and there are certain devices, including I think the one you co-developed, that is now can also be used in the home environment to some extent. What do you think are the main challenges there for further integrating them in the therapy, but also in everyday life?
The exoskeleton.
Yes.
Okay. To begin with, the exoskeleton should be thin, and so the user can sit on a subway in a chair. I think nowadays it is not like that. They have motors on the side, and it is too bulky. This is one thing. So everything is thin, and they have to begin with think about not using wheelchair, and then push the engineers. I think I know how to do it, but as I said, I left 6 years ago. I left Rework Robotics, and I hope they will continue that way. Maybe I can advise them. But the other thing is the algorithm. The Rework's algorithm somehow is better than the others because you don't see any other exoskeletons walking anywhere. So this is one issue.
Okay, thank you. Let's see if we have another question, and we do. Have there been clinical trials assessing the quality of life before and after the usage of this technology? Maybe we can again start with the wheelchair. Have there been clinical studies looking at how this technology affects quality of life?
Well, we haven't finished yet the clinical studies. We made one at the Sheba, which is in Tel Aviv, a medical center, ongoing in the US, and VA veterans. And the one that you saw, the testimonial, it was done. Shirley, yes.
Okay, we seem to be having some connection issues again. Can we please try if we can get the connection back?
Pardon?
Okay, Amit, we're trying to reestablish the connection. Just take a couple more seconds to give it a try.
You are frozen.
Amit, can you hear me again now? Okay, it looks like we've lost Amit for the moment, so I'd say we introduce a short video while we try to reestablish the connection. Amit, can you hear me? Okay, it looks like we've...
hear you.
It's one of the challenges of a virtual symposium. Amit, can you hear me? Okay, it looks like the connection is really unstable. Now I see you moving again. Amit, can you hear me?
Yes.
Okay.
Can you hear me?
Now I can hear you again, yes. I can't really tell you where we got interrupted, but it was regarding the clinical trials regarding quality of life with the wheelchair. And you mentioned there were 2 trials going on.
One was finished and concluded in Israel, Sheba Medical Center, and the other is going on in the US. And we visited, it's not a clinical trial, we visited the Shirley Ryan Hospital, Chicago, and there were the testimonials that you saw were real, not fabricated or something. People really got crazy. And we are all the time, it's ongoing and will continue with our trials, as you saw also, all kind of illnesses, multiple sclerosis and so and so, and we get feedback. So now, since it's going about 2 years or something like that, we continue to improve because of these very important feedbacks, the device, all the time, the feedbacks. And we started to sell it. We are quite sure of ourselves, the device is very good. I'm going to get mine. I was supposed to get it yesterday. I'll get it next week, and then I'll adapt it to the car because I'm driving my car. And I'm so waiting for that because I have problems with blood pressure, sometimes high, sometimes low. So I know that if I can stand whenever I want, wherever, and wherever I want, even for 5 minutes, it will improve a lot of my health.
I'm excited that you will receive it next week. We have one more question from the audience. Is there a possibility to shortly talk about the implemented safety measures in these devices?
Okay, they are inherent part of the device. One is the center of gravity. The person is in all the time in the middle. The other is an algorithm, automatic balancing, the verticality of the user. And now, suppose the user standing and then starting to feel bad, like drop in the blood pressure, then there is a delicate kind of, it does two operations in parallel. One, reclining, and then moving now it's kind of a bed, moving it down. This is one. That are related.
Yeah, unfortunately, again, having some technical issues. Okay, I think you're...
Now I hear some...
Yes, we lost the line again for a moment. You were saying that the wheelchair would recline and turn basically into a bed, right? If I understood correctly, if the pressure drops.
Yeah, it is recline, like, and then takes slowly down the person. This is in case it doesn't feel good or doesn't want to wait for the algorithm that takes up and down. Other things are like giving warnings. We are going to install obstacle detection.
Okay.
But not unlike cars or something that need to see big things. Here you don't. It's very different. We want to see cracks in the ground. Different. And there are more. I wish the software engineer were with me now to explain all the.
I think that's already very interesting features and very useful features. I think we have time for one more question. Can you try to give it back to me, please? I just lost the question. Okay, so being congratulated on your great presentation, and the participant would like to know how it is with orthostatic intolerance in quadriplegics using the up and ride. Do they have a lot of trouble with the orthostatic pressure when standing up? Or is this, I guess, something that takes some training and getting used to as well?
If the person is accustomed to standing, like on easy stand or other standing apparatus, then no problems at all. I'm standing at least 4 or 5 times a week. But if not at all, then you have slowly to train it. You don't have to stand for an hour or 5 minutes. And you can, yeah, I have a personally very good experience, and others also.
Great. We are reaching the end of this question and answer session. Amit, thank you so much also for these very personal insights. Thank you for persisting despite the technical challenges. And it was very exciting to learn that you came from the MRI industry. We are all very much looking forward to your next invention. Amit, thank you so much for being with us this afternoon.
Thank you. I enjoyed it very much.
Thank you. Bye-bye. We are now moving on to our first short talk. The short talk will be given by Diego Paez Granados. He is a researcher at the Learning Algorithms and Systems Laboratory at EPFL and a visiting researcher at the Faculty of Engineering of the University of Tsukuba in Japan. He obtained his PhD in bioengineering and robotics from Tohoku University for his work on robot guidance in physical interactions. Diego's talk will focus on materializing personal standing mobility from design to shared control. Diego, we look forward to your talk.
Thank you, and it's a pleasure to be here. So today I will talk about the work we do between the University of Tsukuba and Professor Kenji Suzuki's lab in Japan and the EPFL and Professor Aude Billard labs here in Switzerland. We do personal standing mobility, work in Quolo, from design to shared control. On this talk, I want to present you a different approach to standing mobility for wheelchair users. As you have seen, there are different devices addressing this standing mobility. In our work, we focus on achieving posture transition through passive system, an exoskeleton that supports the person while standing and achieving standing and sitting transitions, while leveraging for compact and lightweighted device. This design is focused on end users with upper body mobility. The first part of my talk focuses on the passive posture transition. So this is the work we do at the University of Tsukuba with all the team. Here, with a single passive energy storage device, a gas spring, we have designed Quolo to provide assistance in an asymmetric posture transition, which means that from sit to stand, you have a motion of leaning forward, which allows shifting the center of mass, therefore allowing the passive element, the gas spring, to assist the posture transition and to give full power. Then, after achieving standing, if we want to transit back to sit, we do a slightly different motion, a leaning backwards, which allows the center of mass to shift backward and overcome the power of the assistive passive element, thus achieving the sitting posture. This very simple design uses the energy flow from the user, upper body, to the exoskeleton, allowing transferring potential energy controlled by the user's own ability on the upper body, and synchronizes a mechanism that supports both upper body and lower body. We compared an uninjured participant motion on the STS transitions, and we observed the head path. And as you can see, this is an indicator of the center of mass motion. And we can see the difference. There is a significant difference in the path followed with our assistant device and the natural one. But this at the same time is the cause for the device to be able to work with a single and very lightweight system. Current clinical trials are focusing on understanding up to what level of injury can we provide assistance. At this moment, end users up to level T6 of complete spinal cord injury have tested the device, and we are still on clinical work. In here, you can see one of the users trying for the first time, and although the motion is not very smooth, he can still achieve the posture transition without any external power, electrical external power. This difficulty in his motion arises from the actual user inertia distribution over his body compared to the one we use in the design. Therefore, for different body types, it will work slightly different and you will have slightly different motions or difficulties in doing the transition. However, with a more personalized system, we could overcome this difference. And there is a new model of the exoskeleton in which we have improved the assistance, not only for different users, but as well for supporting fully the upper body when leaning forward and leaning backwards, which means that we have a limitation in the upper body support, so that multiple end users would be able to get full required balance while standing or while sitting, therefore increasing the applicability of Quolu. Now we have achieved standing. We are in a standing posture through our passive system. But now, how can we achieve standing mobility? A joystick is an option and is very widely used by many power wheelchairs. However, we hope to give a hands-free locomotion to the user. If we consider these are end users with actual upper body mobility, there is still a possibility of have a hands-free locomotion. And thus we investigate in new control interfaces. We are searching for a way of control simply and reliable through body motions, again to give control to the end user. In here you can see, in this clip, it's a bit extreme, the motion of spinning, but we hope to minimize the effort of the user by using this natural body posture. When you walk, you follow your gaze, and therefore we could achieve a system that learns and personalizes this based on each user. And this is our current work. On the second part of this talk, I want to show you the share control derived from the same principle of simplicity and user autonomy. This work aims to make easier the daily life of wheelchair users by low-level assistance that is significant but doesn't oppose the user intent. There are different approaches in share control, but we follow the simplicity principle of respecting as much as possible the high-level commands of the user, as we assume that the user is smarter and understands the world better than the robot could at the moment. In here, what we present is a near local navigation system. What does this mean? Is near is operating only in the near area of the robot, and local, it only operates in the local coordinate system of the robot, which means operating in the velocity space. We have two layers in the share control model, and the first one is the user intent recognition, which is based on the body posture for defining what is the desired velocity that the user wants to achieve. And second, we have a reactive navigation layer that uses a constraint optimization with tight-shaped representation of the robot that allow us to navigate narrow passages or crowded environments. And this is the one that minimizes the deviation from the user desired commands while avoiding obstacles. In here, you can observe in blue is the user desired command, and in green is the actual executed command after the optimization. This simple test environment designed for evaluation. But now we also can see some tests performed within the EU Crowd project, where we are also evaluating how can we use this system in the pedestrian environment and overcoming a pedestrian or crossing a pedestrian or different situations in which we are required to assist the user. In this case, hopefully, not too common among wheelchair users, but still possible, you can see both distracted and they don't follow each other. Therefore, a collision is imminent. However, the system assists in the collision avoidance and they overcome each other without problem. We observe these trajectories over time, and the potential collision in each point is depicted in green with the pedestrian, and the velocity command space you can see from the share controlled and from the nominal command of the user and what's the actual output of the system. I want to finish now by showing you some of the real-life scenarios that we hope this share control strategy would help to assist end users. And the first one is navigating into normal corridors, crowded spaces. We can see how the robot perceives the world, what are the representations of the robot, but most importantly, we can see how it actually performs and how people also react to the robot. We have to take into account both things. In this kind of situation is where we want to avoid the obstacle, we don't want to collide, but we want to be consistent with the command user, be fluent in the interaction. Therefore, we try to minimize the mental load, which means having an autonomy that contributes significantly to the collisions, while the user fluency remains high, which means that the user intention recognition works smoothly over time, and there is no needing for the user to maneuver too much by himself or herself. Of course, this was recorded before the pandemic. As you can see, people don't have masks, and we are waiting still things to improve and then continue to evaluate in this direction. So thank you for your attention, and now I welcome questions.
We now have Diego live with us in the studio for the questions and answers. Diego, thank you so much for this interesting talk. I have to say, seeing those tests in the Centre Media of EPFL brought back a lot of good memories. We don't seem to have audio. Diego, can you hear me?
Oh, sorry.
Okay, now we do. Wonderful.
This has been illustrative of the work we are doing.
Great. So I have a first question for you, and that is, I noticed, comparing to Amit's talk before, that in your wheelchair, the seated position currently seems to only be possible when there is an external bench or object to sit on. I was wondering, have you also thought about extending this principle to allow seated mobility as well? Or is it already possible?
Yes, this is a very good question. And the initial prototype, the ones that you saw in the video, are made for standing mobility, and precisely only for that. But indeed, we are working currently into having a prototype that could go more into the actual end users, to be a product. And this one would include both standing and sitting mobility.
Can you, related to that, also comment on how easy or difficult it is for the wheelchair user to actually transfer into this kind of wheelchair?
So, yes. So transferring, you mean transferring from sit to stand or transferring into the device?
Transferring in and out of the device, yes. Yeah.
Yes, this in the first exoskeleton that you saw, it was relatively difficult to do it by themselves, because it was a frontal exoskeleton, and therefore the seat is more difficult to achieve. But in the newer design, we have opposed this exoskeleton so that it's easy to transfer from the bed directly to the device. And this has, a significant improvement for having autonomy, full autonomy in the device.
Okay, thank you. I'm just going to quickly check if we have any questions. Okay, I have more for you. One thing I was wondering as well, you specifically mentioned that this wheelchair was developed for persons with upper body mobility. And I see how that plays in when you, in your the second half of your talk, when you show how intuitive it is possible to command the wheelchair. Now, what I was wondering is, persons with good upper limb mobility, you very often prefer manual wheelchairs or maybe push-rim assisted power wheelchairs. Is it possible to somehow combine this? Do you see the possibility of integrating your very simple yet effective sit-to-stand system in a normal wheelchair, manual wheelchair?
Yes, this is a good question. We have had this idea too, and especially for children that they are wheelchair users, that when they start, for example, people with cerebral palsy, CP, we have investigated into that. When they are children, they do prefer manual wheelchairs because they have mobility, they like to move fast and all this. So we have one prototype for children that has the passive exoskeleton combined with a normal manual wheelchair. And in general, the idea is to have a standing mobility. I understand that many people would like to move by themselves when they are still powerful in the upper body, but we still want to have a standing mobility. And this is most compatible with the power wheelchair.
Okay, thank you. Yes. So maybe just one final question before we move on is, you mentioned, I think you really phrased it that way, that for now, the user is still in charge, and the autonomous navigation is just an assistance if you're busy checking your phone. how do you see this evolve? How far along do you think it is before we have these fully autonomous wheelchairs? And do you think actually this is what the users desire?
So that's really a question of preferences. But at the moment, I think in the current society, we want to have this for the current society. And in that sense, people really want autonomy. They want to be able to control what they are doing. And as much as we work into having perfect algorithms, that will not work always. So we humans, we plan ahead much more than what the robot could plan ahead at the moment. And we understand situations that are so variable in the human society. So it is much better for the user to have this level of control and just leave the robot to handle the little things that we cannot see, the little boxes in the ground or the people that come too close and you just don't notice. Because you still don't have this embodiment of the robot, perhaps, then you will not notice how much is really your volume, how much has been changing. And we don't want the user to spend their energy into thinking this. We want them to go and live their lives normally. So we just want to remove this level of heavy mental load.
Well, thank you so much for sharing your work with us today, Diego, and I wish you an enjoyable rest of the symposium.
Thank you very much. It's a pleasure to be here.
Thank you. We will now have a short break and then switch over to the functional electrical stimulation discipline.
Welcome back from the break. Now we will start our second block on the topic of functional electrical stimulation. Here comes a short introduction trailer. right, so it is my great pleasure to introduce our second keynote speaker, Dr. Vence Bergeron. Vence is the CNRS Research Director in the Physics Department at the École Normale Supérieure de Lyon in France. His research focuses on a translational approach for advanced neurorehabilitation therapies in sport, or in short, ANTS, which is also the name of the association he created to provide patients after neurological injuries with state-of-the-art rehabilitation tools, as well as to organize recreational therapies. Vence is a unique observer of the Cybathlon. Being a tetraplegic himself, he competed as an FES pilot in the 2016 Cybathlon and will certainly share inspiring insights on the challenges behind FES and competitive bike races. The title of his talk today is Functional Electrical Stimulation Cycling and Electrifying Sport. Vence, we are looking forward to your talk.
Today I will be speaking about functional electrical stimulation, and more specifically cycling with functional electrical stimulation, which I feel is an electrifying sport, as you can see. The first photo is one's near and dear to me because it is a photo of the very first heat of the very first race in the Cybathlon. So we were the very first ones to be able to race and go. And at this moment, I was in the lead, but they didn't end this as friendly for me. What's interesting also about this photo is it shows someone who's in a tricycle, myself, in what they call a tadpole, which means there's two wheels in the front, one wheel in the back, opposed to a delta, one wheel in the front, two wheels in the back. It's a detail, but it's a tricycle. And the other gentleman behind me, Japanese, he's in a wheelchair, but he's working his legs to move the wheelchair. And so I find that interesting too, because the photo does show the differences in the different types of machines that can be used. However, if we go back in history, we will find a gentleman whose name is Gerard Petrovsky, who envisioned both types of exercise in the 1980s. I show you his picture. I also show you on the right-hand side pictures of his laboratory with the devices. They're stationary devices on the right, and the wheelchair device on the left. So as you can see, 82 was a long time ago. This was thought of, this is not new, but it hasn't been very publicized. The Cybathlon is something that's brought a new light to this, and I'm very happy that they've been able to do that. And so it's an interesting way of bringing technology, handicapped people, and the public together. How does it work? Well, I borrow this schematic, which is a movie clip, which I will show from Kenneth Hunt, who is one of the experts in the field, if not the expert. And I'm borrowing his pictures, his automation, where you find someone in a tricycle like mine, and normally you would send messages from your brain, go through your spinal cord, they would arrive at your muscles, your quadriceps here, push the pedals, and then motion would come from the push on the pedals to the bicycle. However, the problem is, if you have a spinal cord injury, you no longer have that connection. You must rely on an external source, the boxes you see at the back of the bike, which then replace the signal and activate the nerves in exactly the same way that your own intention would when you had voluntary notion. So it's quite simple in principle. It's just a matter of putting electrodes, these are not implanted, they can be, but they're not implanted in this case, strapped over a muscle, and then telling the muscle when it should activate. And it's simple but complicated. Now, to give you some information on the complications, I show you this. This is probably, these stimulation patterns are what we live by in this world. Because when you activate the muscle determines the efficiency of the process. So you see in colors the three different main muscle groups that we activate. The red is the quadriceps, the blue is the hamstrings, and the green is the buttocks. These colors correspond to the circle here, which corresponds to where the pedal is located, the degrees. So 90 degrees is the pedal straight up, and as it goes around, all the way around the 360, you have an angle correspondence. Where you see shaded is the angles that correspond to what you would do to stimulate the right quadriceps on the top, and when you would do it and when you would stop doing it, so that you're pushing only, not pulling at the wrong and right time. So this stimulation pattern is actually unique for each pilot because of the physiological constraints that are on the system. So we live by these patterns. They determine the efficiency and the ultimate speed at which we can go. What makes things more complicated is off to the right, which is cut a bit, but you see that the pattern has been shifted. This is for the same person, but now he's turning at 50 RPMs. So we have to send the signal a little bit sooner, because by the time the signal reaches his leg, he'll be already in another position. So you're seeing a result of the time lag in the signal processing that we have to compensate for. So what we do, at different RPMs, we send the signal at different times so that you get maximum torque so that you can pedal with the most efficient way. So it gets a little tricky, and one has to take care of that notion. It's one of the reasons that limits some of the performance on these systems. Another limit, is fatigue. When we use this electrical stimulation, we don't activate the fibers in the same way as we physiologically would. Off to the left-hand side, by the way, this is a photo taken directly out of Anil's thesis. And on the left-hand side, what you see is small and large bundles in a nerve bundle. The dark corresponds to activation. The light corresponds to no activation. In the beginning, when we want to move the muscle physiologically, we start to invoke more and more bundles, parts of the bundle, and we eventually lead to, when we want to go rapid, activating the larger ones, which are the fast twitch muscles, to go faster. That's the physiological process. However, the problem is when we electrically stimulate, we do the inverse because of the resistance. Lower resistance in the larger bundles allows the electricity to flow better in those, and so we go to those first instead of last. And so as we increase the voltage on the stimulator, we'll increase not only the slow twitch, but the fast twitch also, all at the same time in the beginning. What this means is the muscle will fatigue very, very shortly. There are strategies that are being approached, and one of which is, instead of using a large electrode, we use several small electrodes. And we don't stimulate the entire muscle at one time. We stimulate different areas of the muscle, and perhaps at different frequencies also, to invoke differences so that the muscle does not fatigue. Parts of the muscles are resting while other parts are working, which is more similar to the physiological processes that we see. And with that, you can increase the fatigue factor by about 30%. This was a major finding in Kenneth Hunt's and Anil's thesis work. So that's where we are at now, and it allows you to understand some of the complications in the process that we have to deal with. Now, I would like to also share other elements of cycling electrostimulation, that is the availability of these types of devices. Where do you get them? Well, usually we make them. The reason is because commercially available bicycles are few and far between. What you see on the left-hand side is the very first commercial bicycle that was developed out of Glasgow University with collaboration at Max Planck from Hasumed as the industrial partner, which is called the Ria bike. It no longer exists. It did exist for a few years, but it was not profitable because what happens is the amount of watts that one can produce with this is very low. It's very inefficient. And so when you want to take it outside to ride it, you're not able to do much. You can't go up hills, you can't go very fast, and so it's not very advantageous. That does not mean that electrostimulation is not advantageous. It just means that this bike's performance wasn't to measure. I show on the right-hand side, and again, I apologize for this slide being clipped, but you see the essentials of what I call a hybrid cycle. This is a cycle that has both legs and arm propulsion. Why? Because with the arm propulsion, you have additional watts. So Rick Berkelman, and this is called the Berkel bike after him, invented this, and here's the patent number. The year was in 1980 something, I believe, also. So it's been a while. But Rick invented this so that people who are handicapped like myself but have arm strength can actually do the electrostimulation. At the same time, they're doing the arms, which gives enough power to actually accelerate the bicycle in different environments. In addition, Rick works with people on an individual basis, puts electrical motors into the bicycle also to have even a more of a boost in case that's not enough. And in fact, I worked with Rick on my Berkel bike to have a voice control to change the gears. And we used a lethargic voice control so that we did not have parasite noise, and we had electronic gears so that I did not have to take my hands off of the handlebar. So it became much more convenient to change gears and change the stimulation patterns as I ride the bike. So these bikes do exist, but they're far and few between, and more often than not, they're homemade. But there are many industrial versions of this stationary electrical stimulation, which I show here. The very first one is no longer being manufactured. It was in the 90s. I show it at the top, and it's basically a stationary bicycle. It works exactly the same way that I showed you before. It's just that it's stationary. There's a resistance, which is not coming from the road. It's coming from the electronics or the motor that it's inside of it. And you see the very first one was used very successfully. The problems with it were, the main problem is that you have to transfer to get onto it. You'd have to get off of your wheelchair to get into it. Newer versions, and all of these are on the market today. I'm familiar with each one of them, and I can tell you that each one of them are made professionally on our very good equipment. They have the advantage of you can use them in your wheelchair. You just ride up to the system, you get attached to it, you attach the electrodes, and then you're off and going. And one of the most important things here is the fact that you're building the muscle, and that helps to protect your body. Because when we're set in long times in wheelchair, we can have problems with pressure sores. But if you have muscle to protect your skin and protect it from the bones, you will be able to protect yourself. So there's immediate advantages by doing this. We try to make it interesting by putting a screen and having some animation. That gets better and better as we go on. And in the future, you will see virtual reality systems coming out. There are some professional bicycles that have these virtual reality systems already. And we have incorporated those in our devices here in the lab. So what makes for a lot more fun when you're riding these. All you need is a fan then to make it feel like the wind's coming by. And that works pretty well too. So that's how the state of how it works, what's available, and why we use it. What I'd like to do now is turn to another point that I would like to make. It's sort of the precursor to the Cyberthon. This was thought of by Nick Donaldson and Kenneth Hunt, and it was in the 2005, what they called the university's Sports Day. And here what you see are several paraplegic and tetraplegic riders. Most of them, I think if not all of them, are on tadpole tricycles, home built at the schools, and they're playing a game familiar to a soccer game where they have a pillow that they would each run or use their bikes to throw between the two pillars there in yellow on the other end. And they worked as teams together. So that was an interesting application, I thought. It was a motivation. And motivation is one of the most important pieces of keeping someone involved in a sports activity. And I salute them for doing this. They continued with this 2 other times, once in 2006 and the other time in 2009. And I show you here a photo from one of those sports days where they were racing. So this was the first races against each other. There's 1, 2, 3, 4, 5 people here. There was 11 competitors total. They had 2 types of races, 100 meters and 1 kilometer. The performances are shown here. 29, the raw data, 29 seconds to 86 seconds, which translates to 11 or 12.4 kilometers to 4.2 kilometers per hour on an average, okay? And then there was the 1 kilometer race, which was a bit longer, of course. Now the numbers have been cut, but it's 11 and 2.5, which you don't see on the slide, but they're slightly lower. That lowering is due to the fatigue. It was a longer race, so the average speed was slower. But you're in the 11 to 12.5 range, as you can see. And what we know is that can be improved, and we saw that in the Cyclothon, the very first Cyclothon in 2016. Here you're looking at the podium for the 2016 Cyclothon. You see that the average speeds for the best heats are shown below, where you see the winner at 15.4 kilometers per hour. This was a 750 meter race, okay? So there was some fatigue factor going in, but it wasn't quite a kilometer, but it was close to that. The difference here between these 3 gentlemen are the one who won was actually implanted electrodes. It was the only rider with implanted electrodes, and he was paraplegic. So he had his respiratory system also. The interesting thing is that the other 2 individuals were tetraplegics. So they don't have the same respiratory capabilities. That's one point. And the other point is they used external electrodes, which are less efficient. But it is quite surprising that you're reaching the 11 kilometers an hour, very close to the 15 kilometer per hour mark. Close, but yet not close enough and far. So our objective is to break that barrier. And to break that barrier, we hope will happen in the next Cyclothon. But we've been doing this in Lyon. And here you see a photo of our second Lyon Cyber Bike Day. This is an outdoor photo where we were racing 500 meters. Unfortunately, this has been cut. I have a partner in this, which is the Lyon Free Bike, who helped us organize the race. And you're seeing competitors from Holland in the blue. So it was an international endeavor, which makes it a lot of fun. The speeds that were done by the 4 competitors were 11.2 and 17.1. So we did overcome the 15 kilometer per hour level. But of course, it was only 500 meters, and one must ask the question if the 250 meters extra would have made the difference there. I don't know.
About the electrode? Was it implanted electrode?
No, these were all surface electrodes, and one paraplegic and 3 tetraplegics, myself being one of them, the slowest. So what I will conclude with is an objective. And the objective is for this year's Cyclothon, 2020, which will be held the 13th and 14th of November. So I invite everyone to tune in, basically, because it will be done on a virtual basis this year because of the COVID, which is very unfortunate. But they're doing a very good job of collecting everyone together and organizing, as you can imagine, this wonderful event. And when we look at the FES racing, what we will be looking for is an average speed of greater than 20 kilometers per hour. So I'll leave you with that objective and any questions that you might have on functional electrical stimulation. And I thank you for listening to this talk.
All right, so let's welcome Vance. Thank you for joining us live from Lyon.
Thank you.
So thank you.
Pleasure, and thank you for inviting me.
Thank you. Thank you very much for this very inspiring talk, also on the history of functional electrical stimulation and functional electrical stimulation bike races, and also a very nice advertisement for the Cybertron. So I'll go straight to the point. So you competed in 2016 and you will compete again this year. So will you achieve your target of 20 kilometers per hour?
Excellent question. This year will be 1.2 kilometers instead of 750. So the challenge is even more. But there's a good possibility that we'll be able to achieve.
So then, if I can continue on that, so what will you change in your system in order to reach that, or in your preparation to the event?
One of the main things is the number of muscles that we'll be stimulating. What I showed you before was that we stimulated the quadriceps, the ischio, the hamstrings, and the glutes. What we can do now is to improve the efficiency is to stimulate more muscles. The back muscles, for example, that can help push and give extra torque to the machine. So what we've learned is how to do that, and we've learned how better to stimulate the muscles with the external patches. So with those two advantages, we hope to increase our speeds and our fatigue factor.
Very nice approach. If I may ask you one last question related to the Cybertron. So, what was your perception of the Cybertron competition as a pilot, and what motivated you to take part into it in the first place?
My perception was wonderful. The excitement of being a competitor again, because I rode my bicycle 700 kilometers a year. The perspective to get back onto the bike, to do something that was competitive, was an enormous driver for me. The experience itself was overwhelming in the fact that it was so much fun to see so many people together, concerned about the problem of handicaps, but making it fun too. So I think, and I congratulate the organizers and think that this is one of the most important things that we can be doing to advance technology in this area and help people and individuals in their health and in their both psychological and physiological health.
Thank you very much. So let's now open the question for the audience. So we have a question and a comment. So thanks, Vance, for this great and clear talk. Do you consider FES cycling more as a therapeutic tool or as an assistive device that can support mobility and social contacting, for example, performing sports?
I think both. We have proved that by opening up a sports room in Lyon, which we plan to extend in other cities in France and eventually throughout the world. We do both. We do exercising in an indoor environment so that people can exercise year-round, but we also sponsor exterior events and weekend rides on the bicycle paths that are around our school, and that's a lot of fun. Mm-hmm. So the answer to the question is both. It is a tool that can be used for health, to just improve your body condition, but also a tool that can be used to have fun with your family and ride your bike. As I showed you in the talk, there are bikes that have the hybrid bikes now. We'll hear about another one which I did not mention, but I'll leave that for the next speaker. These hybrid bikes allow us to go out and ride with our families on the bike paths and just to have fun. And so that, to answer the question, it's for both.
Yeah, fantastic answer, and I think that's a great way of trying to combine always these two approaches. I think we have some more questions from the audience. I have one here. So when you design the system, one of your metrics to measure performance is muscle fatigue. So the question is, how do you measure it, and which other metrics do you concern?
The easiest way to measure muscle fatigue is to monitor the amount of stimulation that's needed to maintain a certain number of watts. So we look at the watts that are produced and the amount of stimulation that's required to stimulate the muscle. Eventually, when the muscle fatigues, the watts go down, we increase the stimulation intensity until a maximum of 140 milliamperes, and then eventually the watts go to zero because the muscles no longer produce a contraction.
All right, thanks for the answer. We have one more question for you. Hi Vance, how many channels do your stimulator have? How many channels?
It's a great question. The standard stimulators have 6 channels, 2 channels per muscle. So if you want to stimulate the quadriceps, the hamstrings, and the glutes, you'll need 6 channels, 2 channels, 2 electrodes per muscle. We have a system that works 12 channels so that we can stimulate more muscles, which is back to my first answer. In order to each time we want to stimulate a new muscle, we need 2 new channels because there's 2 channels per muscle.
Thank you very much. I think we have one more question. Yes, so you reach 17 kilometers per hour in the Cyberbike day. What is about the muscle fatigue in that case?
Yes, in percentage, I would say we lost about 50%. How do we calculate that? It's because we measure the speed at every 100 meters, and we look at the decrease in the speed as a function of time as we go around. And what we see is a 50% decrease in the speed of the rider from the first 100 meters to the last. And in our case, that was a 500-meter race.
Okay. More question for you from the audience. So, hi Vance, good news. The Berkel bike is not homemade. Next production is 120 pieces, and the new electronics will be ready for the upcoming Cybertron. It's more of a comment for you.
That's correct. That's correct. That's why that's why I showed it as one of the only commercial available bikes. There's another one that has just come out this year, and we'll hear about that shortly.
Yes, I mean, if I may follow up on that question. So indeed, you mentioned it, getting access to the material is difficult, right? And people have to design it themselves. We'll see as well in the next talk. So how can we make this technology more available and more accepted by the user? What's your take on that?
Yes, we're working on that. One of the issues is price. And it's always a limiting factor. One of the things that we work on in our laboratory, because I do research also, is to decrease the price of these devices. We've been able to do that. The primary problem is the stimulator itself. That's the most expensive piece. Once you resolve that problem, it's quite easy to adapt any bicycle to any tricycle for a tetraplegic or a paraplegic, and there's plenty of them out there. You can adapt in any of them once you have a stimulator. So the stimulator is the limiting issue for the price. We know that we can make stimulators much less expensive than they are available today. So what we'll see in the future is a lowering of the price which will then allow many, many people to do this.
Fantastic. One more question from the audience. Okay, last question. What about the multiple electrodes per muscle group? Are these all driven from one channel?
No, each muscle group has its own channel, which goes back to the first one of the earlier questions. How many channels do we have? Most systems have 6 for the primary 3 muscles that are involved. As you increase the number of muscles, you increase the number of channels.
All right. So thank you very much, Vince. I think it's time for us to move to our next talk. Thanks a lot for joining us today. And also, we would like to wish you all the best for your participation in the Cybathlon 2020 in November. Thank you very much again.
Thank you very much, and thank you, and congratulate everyone involved for organizing these events and making it possible for us as handicapped individuals to participate.
Thank you very much, Vance, for this nice, encouraging message. Thank you. So we now move to our next short talk, also on the topic of functional electrical stimulation, which will be given by Sebastian Tobler. Sebastian is a lecturer at the Bern University of Applied Science in Switzerland. Following a mountain bike accident, he became quadriplegic. To continue to fully live his passion for sports, he started developing advanced technological solutions which are now commercialized by Go By Yourself, a company where he is the CEO. His talk today will be on the recurrent trike with epidural electrical stimulation, and he will present you this technology and how it can be also combined with functional electrical stimulation. Sebastian, the word is yours.
Welcome to my short talk, which I recorded in my backyard to be far enough away from you due to the COVID. I had a mountain bike accident in 2013. This mountain bike accident left me quadriplegic, ASIA B C627, incomplete with no motor function under the injury but partial sensory functions. Back home in 2014, I wanted to get back to nature on a 3-wheeled bike. This bike was designed by me in 2014 and I rode for the first time in 2015. My goal was to combine arm and leg activity, arms for sport and legs for therapy. But how do you combine all 4 limbs with meaningful movement? When we walk or run, the synchronization of the arms and legs alternates. When the left hand is in front, the right foot is also in front. On the right hand is backwards with the left foot. On the trike, the cranksets of the arms and legs are linked by a chain to allow able-bodied limbs to train disabled limbs. The synchronization of the crankset allows you to find the same pattern as walking. Dr. Jérôme Barral from the University of Lausanne pointed out to me that what I had done made sense and opened my eyes to research such as the one entitled Shaping Appropriate Locomotive Motor Output Through Interlimb Neural Pathway Within Spinal Cord Humans, published in 2008. In this study, 12 persons, para and tetraplegics, were asked to stand on a device that links arm and leg movement. If the person on the device moves their right hand backward with the lever, their left foot will move forward. In the rest condition, the patients have their hands on a fixed part of the device and an assistant moves the legs that are on the moving part of the device. Measurements show no leg muscles activity. In the passive condition, the patients have their hands on the mobile parts of the device, which are connected to the legs. The assistant moves the left and right levers of the device, which produces a walking movement of the passive patient. Measurements show almost no leg muscles activity. In the active condition, the patient operates the levers with his arms, which produce an active walking movement of the arms and legs on the device. The measurements show that the legs are active and participating in the movement.
This is especially noticeable in the incomplete quadriplegic person. In summary, the voluntary combined arm-leg movement induces functional muscle activity of the injured limbs in incomplete para or tetraplegics. In 2016, together with a friend, we founded GBY, a startup that makes GoTrike. We made 5 trikes to test this movement with 6 disabled people who were asked to ride for 6 weeks. We did a series of measured and filmed exercises before and after the 6 weeks. Here are our observations. Here you have a person who has a cerebral palsy, on the left before the test and on the right after the 6 weeks. As you can see, his walking speed has also improved. On this exercise, this person needs his cane to get up, and 6 weeks later he no longer needs it. Balance and speed are also improved. Here you have a person who had a cerebral vascular accident. On the left you can see how he walks before the 6 weeks and on the right after the 6 weeks. In the sit-to-stand functional exercise, we can see that he does not use his hand to help himself. Another participant, an incomplete paraplegic, was able to push 25 kg at the leg press when he was released from the hospital 6 months after his accident. He started training 3 times a week in a therapy center in addition to training at home. After a year, he was able to push 35 kg at the leg press, and that's when he did our test. He came back with almost 700 kilometers, but more importantly, he was able to push on the leg press 60 kg. We left him the trike for another 2 months until he reached 90 kg. He told us that his sensitivity had gone from his hips to his knees. To resume, the proprioceptive and motor system are stimulated with the movement. The muscles still functional in the legs of people with reduced mobility will be stimulated and put to use controlled by their own will. We have a trike that allows people with reduced mobility to engage in sports, leisure activities or simply transportation. This activity can be combined with therapy for an improvement in function or an improvement in health. But what if there is no voluntary muscular function of the injured limbs? In 2017, as patient, I joined the STIMO study led by Professor Jocelyn Bloch and Grégoire Courtine. The idea is to get spinal cord injured people to walk again by stimulating muscular activity in the legs via a 16-channel electrode that is attached to the spinal cord. This electrode is connected to the control box or IPG, which is located under the skin at the stomach level. How does it work? The electrode stimulates a sensory nerve linked to a muscle in the spinal cord. This stimulation generates a reflex activity of the muscle concerned. As you can see, without stimulation, it is not possible for me to walk. But if my spinal cord is stimulated via the 16 channels electrode, the walking movement is created. The therapy consists of making the patient walk with the necessary help and that the patient tries to control the movement. Stimulation and movement will generate information which will be traced back through the spinal cord. From the brain, a voluntary command from the patient will go down through the spinal cord. The idea of this therapy is to recreate a network of nerves reconnections. What happened in the lab gave me an idea to combine the EES stimulation with the GoTrike. In 2018, part of Professor Grégoire Courtine's team came to GBY's place and tested the combination GoTrike with EES. And it worked, as you can see on the researchers' faces. The idea was to combine a leisure activity with a stimulation in order to get out of the laboratory. How does it work? There is a stimulator, the electrode, and a sensor that informs the stimulation system that it is the position of the crank, as well as a computer that calculates and an antenna that transmits the command to the IPG. When the user equipped with an EES starts to pedal on the GoTrike, the muscles in his leg will be activated at the precise moment to actively participate in the pedaling. The interest of this combination of trike and EES is to have a muscular activity during a fun activity. This is for people with limbs with little or no voluntary muscle control. I think we are on the right way. This combined activity allows rehabilitation, therapy, or simply taking care of one's health. The advantage of EES is the connection to the muscles, which is done without electrodes to stick on. Today, the challenge is to optimize the stimulation and the hardware to make the GoTrike and EES combination simple and efficient to use. The challenge goes beyond a technical solution, but an active collaboration between researchers, therapists, industry, and patients. This collaboration also allows other research projects, such as understanding what happens when the 4 limbs of the disabled are activated. For this, a device and a researcher were needed. The device was made by my colleague, Professor Kenneth Hunt from the Bern University of Applied Sciences, and the study with people is currently being carried out with Dr. Jérôme Barral from the University of Lausanne. Another study with 30 users is due to begin next year by Dr. Sue Berchi from Swiss Paraplegic Research. The patient, me, the laboratory monkey, initiating projects requires an open-mindedness on the part of the scientist. The only things I have brought with me are my 15 years of experience in industry, the intensive practice of various sports before my accident, and my hours of therapy at home on devices I have bought, modified, or built. These collaborations will allow me to work on other solutions. I hope to be able to talk to you next time while walking through the forest.
I would like to take this opportunity to thank those who have supported me so far, my family, my friends, my colleague at GBY, and of course all the other partners on the screen. Thank you all for listening to me.
Thank you. So let's welcome Sebastian Tobler joining us from Bern. Welcome.
Hi everyone. Thank you. Hi.
I see you're not in your backyard anymore, but thank you very much for this very inspiring and personal talk. So now let's open the floor for some questions. Maybe I will take the first one. So you're taking part in this fascinating trial with this epidural stimulation study. So what motivated you to take part in this adventure? And what is the perception of your progress through this EES stimulation?
The motivation I have would say is going as far as I can with my body to learn this new body I have. I mean, I have not so much control on myself, I mean the legs. And to try a new device, to try a new technology was for me something very inspiring. And I had a lot of experience with FES, and EES opened me a new field of research and test.
Fantastic. Thank you very much for the answer. I think we have a question from the audience. So it's Robert Riener asking the question. So great talk and wonderful slides. Do you consider EES more as a promoter for training and building up muscle force, or is it the crucial contributor during gait?
I think, you know, I'm using both of them. Usually today, I'm using 3 times FES a week and 3 times a week EES. So for me, it's really, I'm someone who really tries to see what can I do with both of them. And both of them have strength and weakness. And today I'm trying to use them in the right way. And it takes time to test, time to measure the results, and time to collaborate with different persons.
I see. Do we have other questions from the audience? Not at the moment. So let me ask you one related to Cybertland. So you like sports, you have a very competitive mentality. So what is your opinion on Cybertland and the competition aspect of it with respect to FES or other disciplines?
I think it's something very interesting in the sense that you are bringing many people, many researchers together. And for me, as you have seen perhaps or understood in my presentation, collaboration is one of the key or the biggest key to have success. And when you can see people together, I know Roger Gasser, I know Vance Bergeron, I have met him. And I think when you can speak together, exchange ideas is the most important thing to go further. And what you are doing is very important, even if sometimes it's not really to just see something on a race field and try to think that you can use it for your daily life. And for me, it's very important to do this integration in the daily life, because seeing something in a race field is something, but looking at it in a daily life is something else. But for me, it's very important what we are doing. So I'm very also thankful that you invited me for your symposium.
Thank you very much for the comment. We have one more question from the audience. What do you see as the main weakness of EES, so epidural electrical stimulation?
So the main weakness, I would say, is how it is used. That means you are stimulating the back part of the spinal cord where you have all the sensitive nerves. And that means when you are stimulating them, you're also influencing all the sensory function who already work. For me, I'm quadriplegic incomplete and I have some sensitive function in my legs. And sometimes using the EES cut off a little bit the sensitive function I have already who works already. So for me, it's one type of the system who is not very interesting.
I see. So I think we reached the end of our time for questions. So I would like to thank you again very much for joining us today, and wish you all the best for also the adventure with your company. Thank you very much, Sebastian.
Thank you very much. Bye.
Okay. So with this, I would like to close this session on FES. I would like to thank all the speakers who participated. And now, before the break, I would like to share with you a short video from Jan Meyer, who is a PhD candidate at ETH Zurich. Aligned with the topic of the Cybathlon 2020, he will share with you his research on user-centered design.
Hi there, my name is Jan Thomas Meyer, and I'm a PhD candidate at the Rehabilitation Engineering Laboratory, or short RELAB, of ETH Zurich. Over the past 10 years, the RELAB has been developing manifold of robotic technology devices for rehabilitation services. For example, we develop wearable robotic assistive technology to be used in daily life for people with disabilities. Developing technology for someone else is always hard. Developing technology for a person with special needs is even harder. Also, oftentimes, the primary end user is not the only person using, for example, an assistive device or a therapy device. There are clinicians involved, but also caregivers or family members. These secondary users are also core for the development and success of novel technologies. In order to make sure that the needs of these users are met, a so-called human-centered or user-driven design is a key success factor of creating high usability devices that eventually make their way into clinical usage or home usage. One of the main Cybathlon goals is the facilitation and exchange between technology developers and the actual target end users. And we've seen already in 2016 and over the course of the last years that this exchange has improved. There are more devices that are actually developed together with the people with disabilities, together with other stakeholders in the device development. This year's Cybathlon Symposium even has user-driven design as its core topic, and we're happy to have a lot of speakers who will share their experience of involving users in the design, what the limitations are, and what the benefits are. The human-centered design process is iterative, mostly because it's almost impossible to get it right the first try. Therefore, being able to say, look, I have not reached all my requirements, the target end user is not happy, I'm just going to go back, start again about the problem, think about the problem, again coming up with requirements and doing a full cycle. With usability evaluation, you can, for example, identify minor design issues that can be solved with a so-called mini iteration. Also, maybe with the evaluation phase, you immediately come up with a new idea and a concept that may be worth trying out because you still have the same requirements. So you see that the evaluation phase is key to the user-centered design. In our online survey, we want to investigate the current evaluation practices and trends of usability evaluation for wearable robotics. We ask our respondents to first of all let us know what their context of use is. We want to understand which target population they develop the devices for, what age, and so on. Also, we want to understand what their evaluation focus currently is, given their technology readiness level. Because we hypothesize that the evaluation focus might shift once you come from an early stage prototype to a more high fidelity, finalized prototype, and eventually a product. It's interesting to further investigate the usage of different kind of measures, because we see that the number of measures being used to assess usability and also the understanding of the term usability varies greatly in our field. For example, we provide a huge list of questionnaires that we know of, questionnaires that assess usability either from a system point of view, from an assistive technology point of view, and so on. So if you develop wearable robotic technology and you have been using different kind of measures to assess target end user needs and make sure how and if your device uses these needs, please go to our website and give us your experience, give us your opinion on the used measures, such that we can maybe see that for a certain context of use, the same measures are being used, and it could even become a standard or benchmark. Of course, we want to share these insights as soon as possible with you, and we already thank you for your time and dedication for our shared purpose. Thank you very much.
Great. So we got the message. If you're a developer of assistive technologies and want to help out Jan, other technology developers, and eventually impact the field in general, please go online and fill in Jan's survey. We will now have a longer break, and we'll come back with the powered exoskeleton discipline at 3:20 Central European Summer Time. See you soon.
Welcome back from the break. We will now start our third block with a short video clip on the powered exoskeleton discipline. Before we move on to our first keynote in this block, we're pleased to show you a short statement from Mark Daniel. Mark joined the IHMC team, about which we will hear more in the keynote, in 2010 and has been training with exoskeletons ever since. He was the pilot in the 2016 Cybathlon, in which he made second place in the powered exoskeleton race. And he will participate again as a pilot in the Cybathlon 2020 Global Edition. Mark will talk to us about the importance of involving users in the development of exoskeletons. Mark, we look forward to your statement.
Hello everybody and welcome to the 2020 Cybathlon. My name is Mark Daniel. I've been the exoskeleton pilot for IHMC since 2010, and as we get ready for the 2020 Cybathlon, we're looking back at the 2016 Cybathlon footage and all the training footage from the three other exoskeletons that we've done so far. And as we've looked through the footage and watched how we've progressed through everything, we've always done a little bit of testing compared to the immense amount of discussion that we have after the testing. A lot of that is them asking very specific questions about the fit of the device, how it moves, its timing, the controls, everything down to the simplest of things by the orientation of how the controls adjust as I move through the different menus. But that's what's made the device work so well for me and really made so much progress in such a small amount of time. In 2016, we've only been working with the EXO for 6 years, and it was our third device, but I only had about 8 weeks of practice before the Cybathlon and really about 8 days with the controls in my hands before we packed everything up and flew out to the competition. I really contributed the success of the device in making the silver medal in the fact that the engineers really listened to the feedback from me and adjusted things accordingly, you know, and proficiently. They didn't argue and think what they think should happen. They said what really looked to be working in application. So I hope everyone else is having a great time testing and training and making their device the best it can be, and we look forward to everybody at the Cybathlon.
Thank you so much, Mark, for this statement. We now move on to our first keynote in the exoskeleton block, which will be given by Robert Griffin. Robert is a research scientist at the Institute for Human and Machine Cognition, IHMC, in Pensacola, Florida. His research focuses on improvement, mobility, and autonomy for leg robotics and powered exoskeletons. Robert received his BSc from Tennessee Tech and his PhD from Virginia Tech in 2017. He was part of the IHMC exoskeleton team that participated in the 2016 Cybathlon and now leads the team that will participate in the powered exoskeleton race of the Cybathlon 2020. He will now provide his insights into a decade of IHMC's powered exoskeleton research and development. Robert, we look forward to your talk.
Hello everyone, my name is Robert Griffin. I'm a research scientist with the Florida Institute of Human and Machine Cognition, and I'm honored to be invited to talk to you all about the work that we've been doing for the last 12 years at IHMC. I know it says a decade, but it's actually been 12 years on exoskeleton research and development. I'm also the lead for the IHMC entrance in the 2020 Cybathlon Global Edition for the powered exoskeleton race, which we're really excited about, and I hope that you all are too. And it's been an interesting time transitioning everything, but I think that it's going to be an awesome experience. So like I said, we've been working on exoskeletons at IHMC actually since 2008. This is our first device you can see here. This is a prototype device with actually the lead engineer on the project running through it. and walking across the room. We've come a long way since then, not just in our production quality, but also in our engineering. So this is Mark Daniel, our exoskeleton pilot from actually our entrant in the 2016 Cybathlon competition. This is just a few days before we left to go to Zurich. You can see, you know, we've really come a long way in that time, and I was going to talk to everyone just kind of the work and the development that has gone into this whole process. It's been a lot, and we've learned a lot of things along the way, and I'm just hoping to be able to share it with everyone. So it all started in 2008 with Mina V0. So we zero index things as good software engineers do. But this was really just a prototype device. We weren't 100% sure what we were shooting for in it. We were just trying to investigate wearable robotics. We hadn't really specifically targeted any kind of mobility disabilities at this time. We were really just experimenting. What is a wearable robotic? What does it look like? What are the technologies that are needed to do this? So along those lines, we kind of just went into it and said, what joints should we power and what joints should we leave passive? So for that, we really powered the 2 main degrees of freedom in the hip, this abduction, adduction, and then the flexion and extension. We also powered the knee, flexion and extension. We included some additional degrees of freedom at the hip rotation and the ankle, just completely passive. Everything was off board. You know, this is 2008. We didn't have the incredible power electronics that we do now and the really good computing and motor controllers that we are available now. So everything was off board. You can see all the giant wires and cables and things. And you can also tell we weren't experts on fit or function or anything like that at the time. We used these really big series elastic actuators that you can see here on the right. Both springs are kind of on the outside, and we use that everywhere. We use the same actuator at all the power degrees of freedom. And this worked really well, so we were able to do good force control. Walking around here, you can see that this is again the same guy from the first video, Gerald, who he's running in the, well, not running yet, that'll be in just a second. He's wearing it just in this kind of zero assistance mode where it's just trying to get out of the way as best as possible. And we thought that this was great. We thought we nailed it. You know, we're done. Wearable exoskeletons are awesome. And so we celebrated. Yeah, we thought we were hot stuff. But then we thought, well, what's the next step? We should try this with someone, you know, who's not able-bodied, with someone who has some kind of gait pathology. But in order to do that, we decided, you know, let's simplify the system a little bit. Let's go purely planar, remove this hip rotation in the ab add. That's just kind of complicates things. We're only looking at walking forward. So let's try and keep it simple. We've never worked on this before. And it worked, you could say. It didn't work great. So here's a video from our first trials in the exoskeleton in this same device, and you can see the pilot does not look comfortable the entire time. He's taking these really hesitant steps. It just, we didn't know what we didn't know as much as we thought we did. But this kind of began this idea of how do we make an exoskeleton that someone who's paralyzed can wear and use and be able to do things that they can't do otherwise. So that has kind of begun this decade of work that has brought us to where we are today. So you can see we started with the Mina V0 all the way up to our newest device, which is Quix, which is really the 5th generation exoskeleton that we have. You can see both the quality of the devices has improved. We've slowly tried different things from fit to what's powered, what's actuated, to overall appearance and structural design. So the first device where we were specifically targeting individuals who are paralyzed is this Mina V1 device. So we had all of our motor controllers were on board, but had off-board computing, off-board power. We simplified it a lot from the V0 device, where we removed the extra degrees of freedom, so it's now just really 4 power degrees of freedom at the hip and knee, and then 1 passive degree of freedom that could be attached at the ankle. Made simple aluminum tubing throughout, just trying to keep things simple with these cuffs, because we didn't really know what we were doing for attachments, so we tried the cuffs here, and it worked fairly well. So we did a new actuation scheme. So we used these harmonic drives where we were aiming for force control. We were trying to actually use the compliance in the harmonic drive itself in order to get a series elastic actuator type form. But from the previous device, the actuators on there were just too big, too bulky. Wearing it was challenging for any kind of pilot. You know, this whole thing, it was heavy. So to reduce weight, we went with this more simplistic harmonic drive scheme. And we ended up just having to do force or position control on the device. We weren't able to get good force control or anything. And then we also tried just using a passive ankle joint, not powered and not actuated, just this passive spring that fit into a shoe that the pilot could wear. For our control scheme, you can see here we just kind of, we would record motions from an able-bodied individual and then we would play them back. So we tried a little bit more complicated of a motion than what our original prototype that we had the video of earlier. We noticed that, you know, the pilot would hit his feet a lot on the ground. We had trouble with this ground clearance, partly because the device would sag and everything. So we really had to exaggerate these kind of motions in order to do motions that we thought could actually work. Then when everything was recorded, we would just play them back on the device. So it was just purely this playback style of recorded then played motions where there was nothing calculated on board. It was just these trajectory lookup tables that the pilot would use, and that was pretty good. We thought that it worked fairly well. It was simple, was the biggest thing, and we wanted to be able to control as much about the motion as possible. The first round of testing that we'd done had been really rough. So this is, again, from the V0 device. But that's partly because this is really hard. You're trying to get these patients who maybe haven't walked in years, and they don't really have much experience being upright. They don't have much experience having weight on their legs or anything like that. This could be an intimidating prospect. So we really were looking for people who had more experience being upright when we were moving to individuals with paralysis for testing. And fortunately, we were able to find two great pilots, Mark and Mia here, who you can see. And they came in a couple different times over the course of a few days in that fall and winter. And we were able to really make a lot of progress with them. So kind of the peak of this, you can see here is Mark walking in the device, just doing this playback style walking with these recorded motions. This isn't the motion that we saw earlier, but notice that having him pick up his feet really high helped a lot on the reliability of this gait. He's still leaning forward really heavily, and that's something that we'd kind of noticed over the course of this device. We learned a lot. We really learned how to work with individuals with disabilities, mainly in the area of how to make the device fit them properly, which is not a trivial thing. It's usually not the main area that you're thinking about when you're thinking about robotics, but that's a critical element. That in padding, how to not have it rub or cause abrasions on their bodies. And you know, we worked with some great orthotists in order to make this possible. But most importantly, probably the biggest thing that we learned in this process was training. So figuring out how to get the pilots comfortable in the device and work with them in order to make progress was really critical. So when Mark and Mia first got in these exoskeletons, one of the things we noticed, they were putting their crutches everywhere. And that makes sense when you step back and think about it a little bit. If you don't have feeling through your legs, the way that you get this kind of proprioceptive feedback with how you're interfacing with the ground comes through your crutches. So putting weight on their hands and then through the crutches really gave them a sense of balance. But you want it to be kind of a controlled motion, so working with them on where to put their crutches, when to shift their weight, when to move the actual crutch motion to time with the device. It proved to be pretty critical throughout this process. From there, we started on our next generation of exoskeletons. So in 2012, we actually partnered with NASA JSC to develop the X1 device. So we didn't really learn our lesson on the very first device, and we kind of targeted too many different things. We thought that we did really well in Mina V1 and that we could grow from there. So with this X1 device, we were targeting more than just mobility and personal assistive. Well, we were targeting more than just a personal assistive device for individuals with some kind of gait pathology. We were also thinking, have this be a robotic aid for lifting heavy objects and even robotic exercise. So you can kind of see in our nice photo shoot down here at the bottom, we had individuals actually do squats and aid their motion with this exoskeleton. So this was a really neat experience. We went back to doing some of these additional motions at the hips. So we added in passive joints for rotation as well as abduction and adduction. The nice thing though, we designed it from the get-go to be lockable. So whenever we wanted to test with somebody like Mark again, we would actually lock out these ranges of motion so that we didn't have to completely replace the hip tube like we did with the original device. So designing it with that in mind, we felt like was a pretty good idea. Another thing that we really started here was actually working on using carbon fiber into our designs. So that's been something that we've done pretty extensively since then, and it's actually surprisingly not expensive. When I think about carbon fiber naively, I typically think that it's a really expensive piece to work with, but if done properly, it's not. And it's really enabled us to keep the weight down since then. We also were aiming, one of the big targets of this device was to get good force control. So to do that, we had a relatively large diameter motor, which went to a belt drive, which then went again back to a harmonic drive, like on the previous device. So one of the things we put Renishaw encoder on either side of this harmonic drive to not directly measure the deflection of the drive, but we were looking at the difference in the encoders in order to actually get the spring force in there. And from a force control standpoint, this was pretty good. The robot was able to do pretty compliant motions. So you can see here Peter messing with the exoskeleton while it's suspended and while it's in zero force mode, and it was pretty good. And then even, trying it on, and we were able to hit, I would say, a similar level of compliance as the original device that had these series of big, heavy series elastic actuators on there. One of the problems that we'd noticed, though, with these actuators is that we had a lot of reliability issues. So they weren't perfect. I'll give more into that a little bit later. So one of the other things that we were really aiming at fixing with this device was the ease of donning and doffing. So with the Mina V1, we had a couple different modes that you could put the device on. You could sit down and then have people physically put it over you, or you could suspend the pilot and then put it on while they're standing there, which isn't great. We did try to put it on in a seated configuration, but this was also not easy. So here's a video of Mark, getting into Mina V1, sped up, obviously. It was not an easy thing, with all these thigh cuffs, having to put those on and then work your way around the shin cuffs and get your feet into the shoes. It was just not an easy task, an easy proposition. That's really limiting when you're talking about both you have a finite period of time that you can test in each day, and you're trying to minimize the time in between runs. Well, part of that is how quickly can you get this thing on and off, but then also just from a practical standpoint, this isn't feasible. This isn't a real device. Like, you wouldn't say that this is a good solution to this wearable robotics problem. So we really targeted to try and make X1 easier to put on or to don and doff. So here we kind of settled in on this design of having this thigh cuff, which is really mainly just a carbon fiber plate that when you let the device hold you, you would kind of lever into, and then a shin cuff in the front that supports your shins in the opposite direction. So this is really what we found. We had these additional straps here that you could wear, but we didn't need them, especially with the fact that you can open the shins. You can actually, they rotate open. It made it pretty easy for donning and doffing. So this is Mark actually putting it on. He's able to just rotate into place. I know this isn't as quick or as detailed of a video as the earlier one, but it highlights that this really just made the whole process much easier. So then when we actually go to test with Mark, it worked pretty well. We're not hitting quite the same speeds as Mina V0 or V1, but that's mainly because not necessarily limitations of the device, but just the amount of testing time. It was able to do it, but we were still using this kind of old pre-recorded gait that was nice. It was functional, but it wasn't what I would call good. The pilot doesn't look super comfortable. You see he's pushing his feet into the ground a lot. He's super lean forward. He's got a lot of weight on his hands. It's just not what I would call a good solution to this problem. But we did learn a lot. We learned a lot on the fit. We learned a lot on how to be able to don and doff. We also learned what not to do. We had a lot of issues with the actuator design, and really we felt like we tried to do too much by targeting something that you can use to help you lift heavy things, that you can use for exercise, that you can use for paralyzed people to walk. It's just a real device that answers some of these problems is probably not going to be able to do all of these. It's not going to be the same device. We needed to target specific parts of the problem again. Because we noticed with this thing, we really had to, even when our able-bodied pilots would wear it, you had to walk like you were walking on ice. And that's because it didn't have this powered ankle. We really wanted to figure out how we could make this gait a little more natural, to get some of the weight off of their hands, to make them a little faster and make the process a little easier. So to that end, we actually developed Mina V2. We decided to focus in on this concept of a personalized mobility device. We weren't targeting adjustability or multiple uses. We were specifically targeting building an exoskeleton that our pilot, Mark Daniel, can then wear for the Cybathlon in 2016. And we think that this is a reasonable idea. You know, if you're talking about an exoskeleton that you would take home with you and would be yours, it doesn't need to be adjustable. It's designed to fit your body. Which is different than necessarily a device that you would use in a clinic or a device that you would use in an outpatient facility where it's a gait trainer. There you're talking about more than one person, so it does need to be adjustable, but we weren't targeting that here. And with that, it really helped. We were able to move to having the motors be part of the structure, so we came up with this new motor actuation scheme, which helped offset a lot of the size and weight of the device, as well as moving to this carbon fiber frame. And then, because it's the Cybathlon, we also had to do onboard electronics and controls. So that kind of led us to this design that you can see here with Mark in it and with this big grin on his face. But we also had to do more than just flat ground walking. We had to be able to go up slopes, stepping stones, go around obstacles, and go up and down stairs, as well as sit down and stand up, which is just a huge variance from what we'd done previously. So the idea was, what can we do to take Mark from this heavily leaned forward position that you see on the left, where he's putting a lot of weight on his crutches, and ultimately it was pretty fatiguing and pretty exhausting, even for someone with kind of this upper body musculature that Mark has, in order to something that's a little more relaxed, a little more natural, where he's not leaning onto his crutches as much to help carry weight, but more just to help modify a little bit here and there to stay balanced, and then also to help feel the ground. And we think that one of the keys to that was adding this powered ankle. So we decided to go for this fully powered in the forward plane at the hip, knee, and ankle. And we used this ball screw driven linear linkage actuator that we call the LLA here, that you can kind of see this awesome exploded view on the left. where it's great because it has this built-in load cell in that mechanism that we're hoping can allow it to do good force control. Fortunately, we never got to that part. We mainly stuck with doing position control for the Cybathlon just because of the competition environment. But you can see here that we located these these actuators just all along the leg, and it's actually their load bearing. So we had this strong aluminum frame that allowed us to avoid duplicating actuator housing and frame and skeleton for the device. But like I said, we really wanted to target this powered toe-off to make walking easier. So you can see we came up with it. We went back to the drawing board and we stopped with this architecture of recording a motion and then just playing it back from an able-bodied person, because Mark's not an able-bodied person. The way he walks is different, and we were trying our best to record a motion that we thought would be successful, but it didn't always work. But we really wanted to make it as easy as possible for him, and we thought that this impulse here in the form of toe-off was critical to doing it. Because if you think about it, a lot of the work that able-bodied people do when they do this comes from their ankle motion, and if you're not injecting that energy from the device, that means that your pilot has to be injecting that energy from somewhere else, which means their crutches, which then ultimately results in a lot more work. So we added in this active toe-off phase here as part of our gait. So we have a defined transfer period now. As opposed to just step with the left foot, step with the right foot, repeat, we actually have a portion of the gait where he is shifting his weight from one foot to the other in this toe-off motion, and then that leads directly into swing. And for swing, we really started doing these kind of foot trajectories as opposed to recorded joint trajectories, because we felt like this gave us much more control over what's going on. And you can really see the effect of this toe-off. So here we have Tyson, who was one of the mechanical engineers on the project. We just wanted to see how long of steps he can take, and we actually turned off the toe-off motion. And you can see it's really awkward. He's trying to hit step lengths that actually are the length of between these lines here, about 1 meter, and he's not able to do it. Even this, big strapping young man that we have here is not able to do it with with being able to use his legs. So adding in this powered ankle, though, we actually were able to largely hit this motion. I mean, it's kind of awkward. The swing is awkward. It's not super natural. He's stepping high. We know that. That part's not perfect, but this was really to just illustrate how important this toe-off phase is to the gait. We then kind of use the same approach for some of the other tasks. So going up slopes, we would design, a heavy toe-off amount, also going down, and then use these foot trajectories as part of it, going up both slopes and stairs. And we think that that was really critical in order for us to be successful here. And then from there, we also had to do this onboard computation, onboard power supply. So we just kind of threw something together. It looks neat and everything here when we stuff it all into the backpack, but in reality, when you unzip it, it was a disaster. This was kind of a last-minute thing. Just strap in what you can. You can see we even threw in a giant capacitor to just smooth everything out. But we also had this user interface, which this was kind of a new thing for us, was how can we design an interface that allows the pilot to easily do what he needs to do. So we had a couple different modes built in. You had flat walking, slope, sit down, stand up, stairs, and stepping stones. And then he had both a touch screen as well as a joystick where you can see on his thumb here that allowed him to interact with it. Because what we were really targeting wasn't necessarily something you would want to sell, but something that would be easy for him to use as part of the competition. So from there, it was just lots and lots of testing. So, you can see here on the left, this is actually the first day of us getting Mark in the device. This was August 8th, and you know, that didn't leave a whole lot of time. We left to go to Switzerland on October 1st, so we had about 8 weeks of actual testing. And when you consider that he hadn't been in an exoskeleton for 4 years, so that didn't leave a whole lot of time. And it's not like we could do just testing the whole time. We actually had to tear the exoskeleton down a couple of times to fix problems with electronics or fix mechanical issues or repair parts. So this is kind of a video of us. It was a late night of us all just pitching in to rebuild the device, I think to handle some communication problems. But one of the keys was just to make the best of the time that you had in the device. That meant testing, and more testing. So there's, you know, testing slalom, testing stepping stones, testing stairs, testing slopes. And we just tried to squeeze in as much testing as possible during this time period. And this is something I can't say enough, is that we were enabled by having an incredible pilot in the form of Mark, where I'm pretty sure, regardless of what the case was, he was going to get across the finish line. It doesn't matter if he was dragging the exoskeleton along with him to do it, but he was going to make that possible. But this was actually the fun part, where we got him in it, and you realize that all of this stuff that you think works great when you're wearing the device doesn't necessarily work so great when you put someone who can't feel his legs and has no sensation in the device. So, for example, we decided, what if we, instead of prescribing a toe-off trajectory for the ankle, just say push with this much force at the ankle? And when I wore it, and when Tyson, one of our other engineers, wore it, we both thought that that was the best idea. We thought that it would work fantastic. And it turns out when we actually put Mark in it, he didn't like it. We noted that for him, having this rigid position in the ankle really helped him stay balanced. He knew what it was going to do when it was doing it, and he was able to just work with the device. Kind of like when we drive a car, it becomes an extension of your own body. That's where we were trying to get to with the exoskeleton for him. And this worked well. We were able to come in second. We were incredibly fortunate in doing so. I mean, we did a lot of work. We had a great team. We had a great pilot. But there were a ton of other great teams there. I can't say enough about the ReWalk teams and the South Korean teams and just all the other teams that were there. This was an incredible experience, and I'm sad that we don't get to repeat it in 2020 with everybody being there, being in this environment, but I'm excited to see what we do with this international format with the global edition. But probably the best part about it, the competition, was actually going out and taking the device out afterwards. So here's Mark walking around Zurich. Both, you know, we went to this incredible church, and we were walking along the river, and it was really just an amazing experience to get him to actually take the device out into the real world and use it. It's not just it doesn't just work in a competition, it actually works in the real world. And I think that this was very meaningful, because it says that we're not just creating devices that are good for competitions. We're not just creating approaches that work in a constrained environment, but these are real devices that can help real people go places and do things that they can't do otherwise. But the big question for us was, what was the next step? And for that, we developed this new exoskeleton, which is Quix, building off of our Mina V2 design. So you can see here, this was also targeted for the 2020 Cybathlon, but also the Toyota Mobility Unlimited Challenge. So we've been really fortunate to be finalists in that competition, and we're able to combine our efforts for both Cybathlon and Toyota. Some of the big improvements of this device is better packaging, so we greatly reduced the size of the backpack. And I think that this is important. And not only does it make moving in the device less cumbersome, you know, you have a lower inertia by packing everything in closer to his back, it also moves the center of mass closer to his torso. One of the first things we noticed when testing with Mark is we didn't have to have him pitched forward as much, because the weight is closer to the center of the device. So this was really important because it enables him to have a more natural upright position when walking. But also, from the design, we're able to do much more easy battery swapping. before we had actually an electric bike battery in the backpack. You had to physically unzip the thing to remove it. Now we can just hopefully hot swap them, slide them on and off. And we also added in this powered abduction-adduction. So after our success with the idea of adding in this powered ankle, the thought came, well, what's the next thing that we can do to reduce the work that our pilot actually has to do when walking? And it was adding in this lateral motion. So, you know, during natural walking, you have a slight sway in your center of mass as you go over your feet when you're walking, and otherwise, you know, these pilots are having to replicate that by putting forces out with their crutches. So by allowing him to shift the motion laterally, he's able to really minimize the loading that he's having to do with his crutches in order to maintain balance. We also really decided to push forward with this better user interfacing. So instead of using the backpack straps that we'd used with all of our previous devices, we went to a more large strap that goes across his stomach. And this was great. He really thought that this was just way more comfortable. One of the problems, though, that we noticed is we had to introduce some additional straps in there in order to actually give him better control of the device. So with the shoulder straps, he was able to lean into it and really had good body interfacing and control and be able to manipulate the weight and the loads on the device. With this, he wasn't able to put that torsion with his shoulders, so he had to go with an additional strap across his chest in order to give him that. And we've been testing a lot. So here, you know, this is from a couple weeks ago, in case you can't tell by the masks that we're all wearing, trying to stay safe but still stay productive. We're able to really push forward on some of it. He really has been raving about how much easier he thought the new device is with his gait, and we're really pushing forward to try and do a good showing for this next Cybathlon. Both with slopes and stairs and then just flat walking, and then also still having a little bit of fun as we're going. You can see here we just decided to have him try out a skateboard. But I think that the biggest takeaways from this for us has been making sure that you have the pilot in there early and often. Obviously within safety constraints, you know, make sure that everything's safe, but developing these devices is an active feedback process where you'll try something and it will work for you, but then when you put the pilot in, it doesn't necessarily work. So making sure that you're involved in that process has been critical. So making sure that the pilot is involved in this process and then you iterate often and quickly has really been critical. Another key to the success has been, you know, we've had an amazing team over the years, you know, different faces coming in and out from 2008 to now 2020, but that's really been amazingly rewarding. And then there's the man behind the camera who's captured all of this, who you don't get to see too in some of the videos. So thanks to William to be able to make all of this awesome recording and awesome pictures and media possible. And then having a great advisor in Peter Newhouse, who really built this program up, and a great pilot in Mark, has been really huge to making sure that this has been successful and making sure that we've learned a lot. And with that, I'd like to thank you all for listening, and I hope that I said something worth listening to. I hope that maybe someone learned something from our experiences throughout this whole process, this, you know, slightly over a decade that we've been working on it. And I'd like to also, again, thank the organizers for, despite all of the setbacks and challenges that we've had, really coming together to put both the symposium and then the upcoming global edition of the Cybathlon together. This wouldn't be possible without you all and your vision in order for making such an event come to fruition. And I'd like to open the floor up to any questions, and I'd love to hear from you all.
We now welcome Robert Griffin, live from Pensacola. Robert, thank you so much for this talk, for sharing this beautiful journey of 12 years, beautiful pictures, really beautiful videos. I think it was definitely something in there for everyone. I don't have, okay, there we go.
Over the hurricane that hit us.
I was just about to say, Robert, we understand that your area has been hit by Hurricane Sally. Power outage, among all the things. we prepared for. This was not on our list, so we really appreciate that you tried very hard to be with us here now. Thank you so much for that. How is the situation currently?
Things are going pretty well. Everything's kind of stabilized. Water has come back for the most part. We're still waiting on power, but fortunately I charged a few batteries ahead of time, so.
Great. I want to start with a first question. You showed this beautiful journey across these 5 redesigns, basically, or 5 different designs of exoskeletons that you've developed. And I was wondering, with all this experience, you know, do you have anything, a secret ingredient that has stood out that you would give along to anybody who's entering this field and wants to develop a new exoskeleton? What would be the key thing that you learned that they should focus on? Is it that capacitor, that big capacitor in the backpack?
No, I would say some of the big things are really focusing in on the motor design from the beginning. Everything kind of builds from there. That's the little central part of the entire exoskeleton. So making sure that it's reliable and that you have good motor controllers and power electronics in order to actually operate it is pretty essential. Thinking about power density is always a challenging problem. You're never going to be able to hit the power density of human muscle right now, maybe in the future, but right now you're just not going to be able to do that. So doing the best you can in order to get things to be relatively light, but also strong is pretty key. But then making sure that, like I said, the device is reliable from the beginning so that you're not, 4 months in to having a fully assembled thing, having to debug what's going on with your motor still. That's a pretty big showstopper as far as being productive and actually making progress. So making sure that part, if you have to have anything functioning well, it's your motor.
Thank you, Robert. Let's see if we have any questions from the audience. Okay, we have one. Thanks for the talk. How much work was put into the physical attachment system? How did you work around the problem that the user can't give you much feedback below the injury?
So a fair bit of work was put in there. We definitely tried a lot of different things. One of the keys, I think, is to bring in the experts in that area. So I'm not an expert on prosthetics or orthotics, so actually consulting with people who's made that their profession is pretty essential to make sure that the locations of these contacts are in places that aren't going to endanger the pilots or users. But then observing what even though they can't necessarily feel what's going on, there are indications if things are bad. So swelling, reduced circulation, all of those are signs, abrasions. You can see that in inspecting after every use of the device, particularly in the beginning, in doing these kind of physical checks to make sure that you have a good interface and that it's not harmful is really essential, because the last thing that we want to do is, have a device that ultimately ends up hurting the people that we're trying to help.
Great, thank you. We have further questions. What do you think is the most technical issue in your latest powered EXO? Which metrics do you usually use to evaluate your device? I guess the biggest technical issues, I would say, are it's still not balancing. So we don't have this kind of active balance in there. We're able to do passive balance, lock the ankles, and then Mark can maintain his own stability via his vestibular system and the crutches and everything. But we're not actively doing that as a feedback problem, which is funny because that's something that, our group and Florida actually kind of considers ourselves experts in, is this idea of balance. But we're just not quite there yet, I think, from a reliability perspective, because there's so much uncertainty in the system. You have this human who you can't measure everything. So there's this, from a technical perspective, there's this big, what are your feedback inputs and your outputs problem that is currently just unknown. And
trying to work towards that. I'm not 100% sure what the answer is going to be. I think adding additional sensors at the feet and via like IMUs for feedback in order to estimate these kind of parts of the system is going to be a major step forward, but was just a little outside the scope for this portion of the challenge.
Absolutely, and we will actually have in our second short talk some exciting work in this direction. We have another question from the audience. Do you think it is necessary to have 100% assistance at the ankle during toe-off phase to get the benefits you observed, or would 50% assistance already suffice?
If you could add in, if by 50% you mean some of it comes from some kind of passive energy storage mechanism like a spring, I think that would actually be a great way forward, particularly from a commercial device perspective. You know, that reduces the requirements for actuation at the ankle, which also probably will reduce distal mass. Everything gets improved up the kinematic chain from there. So that's a great potential option. We just, for the kind of control that we wanted to do, we didn't want to potentially be limited down the road. So having the ability to do 100% assistance, we thought was important. It could be that, you know, as we move to looking at the ideas of how you can commercialize these kind of technologies, that's a great potential avenue for doing so.
Thank you. Do we have further questions? Great to see the user pilot involved with the device development. What strategies would you suggest for recruiting and inviting the pilots to participate? How did you find Mark, and how do you, make this worth his time?
So I guess I'll start with the way that we found Mark was actually going around to some of the rehabilitation and outpatient facilities and asking if they had recommendations for individuals who were, kind of looking for, who were, bold, willing to look to potentially try out new things, who also responded well to the gait training. So Mark had used kind of the past cases and had experience being upright. And so that gave him a little bit more comfort with this device than somebody who had not had that opportunity recently after his injury. So that way he never completely lost the idea and feeling of being upright, which is good. I think that meant that it wasn't like this 10-year time lapse where he couldn't remember what that sensation was, and then it resulted in being completely foreign to him. Our ability to get him involved. So Mark is actually a full-time employee with us. So his background is in a lot of machinist work, mechanic work, things like that. And we need that. We need that skill on site. So he actually built a number of the carbon fiber components in the exoskeleton. So, which is kind of cool to say that he helped build the physical device that he's in. And then, we have some other projects that he's helping with from a technician perspective. And then always soliciting his feedback. It's great. Now he's been doing this for, I guess, since 2012 or 2010. So he's had 10 years of experience. So he's potentially more experienced in working with exoskeletons than I am. So he really knows kind of what we're looking for in a lot of ways. So soliciting his feedback and making sure that he knows that he is every bit as much of a member of the team, if not more so, than the rest of us. And his opinions on this are extremely important because he's the ultimate end user in it. I think that's been pretty critical.
What a beautiful example of user-centered design. So we unfortunately have to stop here and move on. Robert, again, thank you so much for being with us. We hope that the situation stabilizes and recovers quickly. And we wish you and Mark and the entire team all the best in your preparations for the Cybathlon in 2020 in November, and good luck with the race.
Thank you very much.
We now move on to our first short talk. And I just have a slight technical challenge here, so I'll take advantage to just say that it's been pointed out to me that it looks like I'm reading text messages during the talks. That is, I can assure you that is not the case, but I have my backup questions stored here. So now it's my pleasure to introduce the first short talk speaker, who is Chiara De Vittori. She's a doctoral student at the Rehabilitation Engineering Laboratory at ETH Zurich. She obtained a bachelor and master in health sciences and technology from ETH Zurich with a focus on medical technology. During her master's thesis at the Rehabilitation Engineering Lab, she worked with the ViroLeg, a gait exoskeleton with variable compliance in the knee, which participated in the Cybathlon 2016. She will now present the work she performed during her thesis on the gait analysis of ambulation on even and uneven ground with a stiff or compliant exoskeleton. Chiara, we look forward to your talk.
Good afternoon, everybody. My name is Giada De Vittori, and I'm a PhD student at the Rehabilitation Engineering Lab of the ETH Zurich. Today, I present you our work on gait analysis of ambulation on the even and uneven ground with a rigid and a compliant exoskeleton. So, as you might know, power lower limb exoskeletons might be a solution to allow spinal cord injured people to walk again, therefore restoring the ability to perform ambulatory tasks of daily life. And at the moment on the market, there are some exoskeletons for everyday use, such as the Rewalk and the Indigo that you can see in the pictures. However, most lower limb exoskeletons do not perform well on the uneven ground, and since the chance to encounter irregular surfaces during community walking is pretty high, then this is a problem. Coping with the irregular ground is kind of easy for able-bodied people. So what might be the difference between the human and the exoskeleton's leg, which then leads to the problem? It is thought that to walk on the uneven ground, compliant legs, like the human's one, are required. And compliant means that the joints allow a deviation from the target trajectory in response to external forces. And for exoskeletons, these external forces can come from the user or from the environment, for example. And if we look at lower limb exoskeletons, most of them have stiff joints as a result of the high reduction ratio of the actuators. And therefore, this may be the limiting factor when walking on the uneven ground. Right now, compliance has already been added to robots, like bipedal robots, or to prostheses or exoskeletons used in the rehabilitation field. And in rehabilitation, compliant exoskeletons already gave positive results, such as better interaction with the user or higher adaptability to the environment. The problem is that these exoskeletons are stationary, or they are meant to be used in a controlled environment, such as the clinic or the lab. And therefore, despite the positive results in the rehabilitation field, the effect of compliant joints on the gait of spinal cord injured people working with lower limb exoskeletons for everyday use, it's still unclear, especially on the uneven ground. To investigate this, we developed the ViroLeg, which is a power lower limb exoskeleton with compliant knee joints. The ViroLeg has active hip and knee joints and passive ankles. And what's special about the ViroLeg is that the actuation of the knee can be switched between compliant and rigid, and this by inserting or removing a bolt that enables or disables the spring mechanism that then makes the knee compliant. In this way, you can basically directly compare rigid and compliant conditions with the same exoskeleton. The ViroLeg has already been used during the Cybathlon race in 2016, and there it was already used with the compliant mode. So let's go back to our research question, namely, are compliant exoskeletons an advantage for spinal cord injured users? So our hypothesis is that compliance can bring advantages to paraplegic users, especially when walking on irregular surfaces. More in details, we think that compliant exoskeletons have the potential to increase performance and to decrease the effort for the upper body in maintaining balance. So basically, less effort while using the crutches. And this, as I said, compared to rigid exoskeletons. To investigate our hypothesis, we analyzed the gait of a paraplegic pilot walking with the ViroLeg, with both the compliant and the rigid configuration over the even and uneven ground. So we ended up having 4 different conditions. More in details, we divided our study into 2 blocks. We started testing the compliant configuration, and after that we tested the rigid one. For both configurations, we performed 10 training sessions with the paraplegic pilot, where he had the possibility to get used to the exoskeleton. And after these training sessions, we performed 3 test sessions where we recorded the data. During each session, the pilot walked around 10 times on the even and 10 times on the uneven ground. So we set up a track so that the pilot started walking straight at a self-selected speed on the uneven ground. Then he moved to the beginning of the uneven ground, and when ready, he walked on it. And after this, he went back to the started point where he could sit down and take a break of like 2 minutes, and then he started another round. We evaluated only the straight walk, so the transition from one ground type to the other, which in the sketch is represented by the light gray arrows, this was not considered. During each session, the subject performed around 10 of these rounds, and one session lasted around 2 hours, and we could perform 1 or 2 sessions per week. Here is a picture with more details of the setup. As you can see, the uneven ground was simulated by a wooden board of 2 meters length, with steps of about 3 centimeters height placed at irregular distance. On the tip of the crutches, which were needed to keep balance, there were force sensors that recorded the ground reaction forces of the crutches. Then on the pilot, on the varileg, and on the crutches, there were markers so that kinematic data could be recorded with a motion capture system. And then, as you can see, 2 spotters were always walking close to the pilot for safety reasons. So what are the results regarding the hypothesis of compliance leading to higher performance and lower effort? Today I will present you only the main results that we obtained, and one of these is walking speed. As you can see in the plot, with the compliant configuration, which is blue, on average the pilot could walk faster on both ground types. So it's interesting to notice that also on the uneven ground, with the compliant configuration, on average the pilot was faster than with the stiff one on the even ground. So the higher speed is mainly due to longer strides. We can see that stride length follows the same trend as speed, with the compliant configuration allowing on average longer strides, even if the step length settings for the EXO were exactly the same. Despite the walking speed reached with the compliant configuration being on average higher, this is still lower than the speed considered to be the minimum for limited community ambulation, which is 0.4 meters per second. But anyway, according to our results, we can say that with the compliant configuration, the pilot could, in average, reach higher walking speed and longer strides. Therefore, it could perform better than with the rigid one. To investigate the effort for the upper limb in maintaining balance, we looked at the ground reaction forces of the crutches. And from these forces, we calculated the impulse by integrating the forces over time, so over a gait cycle. And our hypothesis is that a lower impulse corresponds to lower effort for the muscles of the upper body. This because it basically means that over time a lower total force is exerted. And here we can see that for the impulse, the ground seems to play a higher role than the configuration. The impulse on the even ground is clearly lower for the compliant configuration than for the rigid one. And on the uneven ground, the difference between compliant and rigid configuration is not so big, but still significant. So considering the lower impulse, we can say that working with the compliant configuration requires lower effort for the pilot if we compare the same ground type. In conclusion, according to our results, we can say that compliance leads to higher performance and lower effort for the subject, and therefore it might be a more efficient configuration to use when working with a lower limb exoskeleton. Then the subject was also saying that walking with the rigid configuration was really less fluent, while walking with the compliant one felt more natural and it was easier to keep balance, and this might also be supported by the lower impulse with the compliant knees. Therefore, we can say that compliance can really bring advantages to the subject, both in daily life and in the rehabilitation environment. And this because increased performance and reduced effort might allow weaker spinal cord injured subjects to use the exoskeleton, and maybe also for a longer time. In our experiment, we tested only one pilot, but we really think that it's worth to continue investigating compliant exoskeletons for spinal cord injured people, because compliance may really improve the usability of lower limb exoskeletons for daily activities. So thank you for your attention, and I'm now open to your questions.
It's now my pleasure to welcome Chada live from the top floor of this building, and we are actually broadcasting from the very lab where this study was performed. Chada, thank you for being with us today.
Hi, thanks.
Chada, in your study with one pilot, this study involved training over multiple weeks and many adjustments. What kind of feedback and input did you get from the pilot along the way, and how did you incorporate this in your work?
So, yes, we basically trained and measured over 4 months. So also the pilot had to put really a lot of effort into that. And it was always really positive, and it gave us a lot of feedbacks. And also we maybe couldn't implement all of the feedbacks like at the moment because we were already testing, but I would say that it could give us a lot of feedbacks on the trajectories that we implemented in the exoskeletons, and also on the posture, on the position of upper body. So some of these feedbacks we could implement so that it could work in a more comfortable way, and yeah.
Thank you. Let's see if we have some questions from the audience. Okay, we have one here. Thanks for the interesting talk. I wanted to ask what the main difference in the walking strategy of the pilot was when walking in the compliant or in the rigid motion.
So the main difference was the posture of the body. So when walking with the rigid configuration, the pilot was leaning much more forward with the trunk and with the whole body, and this caused him to have a lot, so more weight on the crutches than on his feet, and this probably led to the higher impulse, and then also to more effort for the muscles of the upper body when walking.
It's an interesting point that was also brought up by Robert before. Do we have further questions? Great work. Do you think adding compliance to more joints, for example, the ankle, will lead to even better performance? Are you planning on adding compliance in more joints?
So in our case, the ankles were not actuated. They were kind of, they had a spring on it to improve foot clearance. So they were not really rigid. They could a little bit adapt, for example, to the uneven ground. But yeah, maybe adding compliance to the ankle, I don't know if it would help, but for sure, like it was said before, adding these active ankles would for sure help more when performing the steps.
Or maybe this combination of the passive compliance and an actuation. Yeah.
Exactly.
Do we have further questions? Thanks for sharing your results. How stiff was the spring, and did you check the effects of the stiffness of the spring on the results?
So for the compliant configuration, no, the stiffness of the spring was 206 Newton per radians. I don't know the stiffness of the rigid configuration, but it was actually higher. And basically, we didn't really looked at the effect of the stiffness of our results, besides really comparing the two configurations, so the different stiffnesses.
So how was the stiffness level you used? How was that selected? You said you didn't compare different levels.
So for the rigid one, it was selected so that it was really stiff and that no deviation were allowed, basically, from the target trajectory. While for the compliant one, we choose a stiffness that was stiff enough to support the pilot during stance, but anyway compliant enough, so soft enough to optimize the energy during the swing phase. So we did it tests on basically on a test bench, and then we selected this stiffness that we then use in the measurements.
Okay, thank you very much, Chada. We will move on to our next short talk here. Thanks again for being with us today.
Thank you.
We now move on to our second short talk in the exoskeleton block. Our next speaker is Jemina Fazola. Jemina is a doctoral student at the Laboratory for Cognitive Neuroscience at EPFL in Lausanne. She received an MSc degree in bioengineering from EPFL in 2014. Before starting her PhD in balance control, she worked as a research engineer in the TWICE project and was part of the team that participated in the powered exoskeleton race at the Cybathlon 2016. She will now talk to us about the adaptation of postural strategies during standing in a locked ankle passive exoskeleton. Jemina, we look forward to your talk.
Hello everyone, and thank you to the organizer to giving me the opportunity to present my project, which is about balance control strategies during standing in a locked ankle exoskeleton. So about 5 years ago, we started to develop this exoskeleton called TWICE. It is done for complete spinal cord injured user. And as you can see here, our pilot can don it on by herself. She can trigger the motor and she can stand. This exoskeleton has only 2 degrees of freedom per leg at the hip and the knee joints. And the ankle is completely locked. To compensate the lack of mobility of the ankle, we use a curved foot sole to achieve a quite natural gait pattern. As you can see here, the pilot can control the exoskeleton thanks control button on the forearm of the crutches, and she has visual feedback on a smartwatch. It is important to notice that she is starting every step by pulling the trigger. Here, even when climbing stairs, she's triggering every step. When we were designing this exoskeleton, we had to make some trade-off between complexity and functionality. And we decided to decrease the number of features in favor of leanness and also lightness. But of course, with only 2 degrees of freedom per leg, we need the crutches in order to keep the balance. During the past year, we tried also to do a lot of daily living activities, and we noticed that the crutches were really a drawback when standing. That's why we decided to develop a standing postural controller, and we thought that we could use the lateral passive stability thanks to the distance between the feet and only control the exoskeleton in the sagittal plane when standing. So in order to develop this controller for the TWICE exoskeleton, we use a bio-inspired approach, which means that we developed a passive exoskeleton that we call Inspire, and that you can see here on the video. So it has the exact same structure than the TWICE exoskeleton, but instead of having motors, it has passive revolute joints at the hip and the knee. And the goal was to see how able-bodied participants will adapt to this kinematic constraint and to identify the balance control strategy that they use. And then to implement this strategy on the TWICE exoskeleton. So for this purpose, we asked 5 healthy young participants to stand in the Inspire exoskeleton. And it was done under 5 conditions. For example, eyes open, visual feedback, cognitive load, random perturbation, or eyes closed. And the goal of this condition was really to trigger a range of perturbation in terms of intensity, but also we saw that under different conditions, different strategy might be used. So we know from the literature that already different control strategy exists to keep the balance. For example, the ankle strategy, where you mainly use the torque of the ankle to keep the whole body balance. There is also the hip strategy, where you use the trunk in order to reposition the center of mass. Or there is this less known strategy that is called the vertical strategy, where you basically bend your knee and bring your trunk forward in order to keep your balance. And this strategy is mainly observed for backward fold. Of course, for our exoskeleton, the ankle strategy is not possible, but we could use the hip strategy, for example, by using the rolling property of our curved foot sole. And similarly, the virtual strategy, the curved foot sole will compensate the lack of mobility of the ankle. The next step was really to identify this strategy in our data. And what we did is a segment analysis, which means that we looked at the trunk motion, at the shank motion, and we looked at how these 2 segments were correlated with the center of mass motion. So we know from the literature that the shank segment and the trunk segment are positively correlated with the center of mass displacement in the vertical strategy, but that in the hip strategy, the trunk segment is negatively correlated to the center of mass motion. So only by looking at these 2 signs, we can distinguish between these 2 strategies. We looked also at the determination coefficient, and this gives us an idea of the percentage of the center of mass variance that is due to the shank or the trunk motion. And to summarize the result, we found that the participants mostly spent their time in the vertical strategy, so this is the pink dot on the graph, except during random perturbation where they use the hip strategy. And this is not surprising because even without any constraint, the hip strategy is preferred when the intensity of the perturbation are higher. We also noticed that the shank was mostly contributing to the variance of the center of mass. So we could conclude that the participants mainly regulate quite standing balance by flexing and extending their knees, and this is in order to affect the shank and the feet angle. And thanks to this result, we could develop a standing balance controller. So this controller used the center of mass position in the sagittal plane to fit the controller, and the controller is regulating the knee angle. And you can see here that it can sustain small perturbation. Also, the exoskeleton was intrinsically unstable, so when the controller wants to turn it off, it will fall. Then we tested it with our pilot, so she's a complete spinal cord injured user, and you can see that this controller can sustain quite dynamic perturbation. So this video is only preliminary result. With my colleague Romain Beau, we are now working in an experiment with more control and experimental condition like quiet standing, pulse perturbation, static perturbation, and also object lifting perturbation, as you can see here on the video. But this was just a test, that's why she's using this kind of object. So with that, I'm done with my presentation. And before finishing, I would really like to thank our pilot, Silke Pan, for her contribution, but also for her patient and also all the TWICE team. I would like also to thank my advisor, Mohamed Bouri, Hannes Bleuler, and Olaf Blanke. And now I'm ready to take your questions. And also, if you have more questions after the talk, don't hesitate to contact me or any member of the team. We will be really happy to answer your questions. Thank you very much for your attention.
We now welcome Jemina live for the questions and answers. Jemina, thank you so much for this exciting talk, which is beautifully aligned with the last statements that Robert made in his talk.
Thank you very much for giving me this opportunity to present my talk.
A first question to you. You pointed out that you were not able to implement the ankle strategy, and we've just heard before about the importance of the ankle and this degree of freedom missing in most of the exoskeletons. How critical do you think is it towards your goal of removing the need for crutches in standing?
So indeed, the ankle is really like a hot point if we need it or not. And for us, we really choose to decrease the number of complexity in order to have a really light exoskeleton. And as you can see, by using like this kind of bioinspired approach, we can adapt to any kind of configuration. So we could see that we don't really need the ankle. But of course, we saw that during the gait, especially during working on an event terrain, it will be very great to have it.
How do you think this strategy could also be applied to an exoskeleton that doesn't have that rounded off foot the way you have it? Is that critical to your approach? Sorry.
I think it would be super interesting to try exactly the same approach with a passive ankle, because I think this vertical strategy where you simply use the knee flexion in order to keep the balance could work also with a passive ankle. So I think it's really a step that we should maybe do and try a passive ankle on our exoskeleton.
Thank you. Let me check if we have any questions. Not right now. So I'll continue with a couple of mine. This was standing balance. What do you think what is the biggest challenge to extend this towards dynamic balance?
Well, I think for dynamic balance, if we would like to get rid completely of the crutches, we need more actuator. We need to actuate this exoskeleton also in the lateral plane, and this adds also bulkiness. So it's always a trade-off, because I think Dr. Goffer at the beginning of the talk said that if we would like to take the exoskeleton outside of the lab or outside of the clinic, it should be lean. So that's why we made this kind of choice to really reduce the complexity. And also we saw in other talk, by reducing the complexity, sometimes we also increase the reliability. So, for example, a passive ankle could be great, but it might also give the user less trust, because it's less reliable and less predictable. So I think sometimes stiffness and low account actuator exoskeleton can be more trustable, maybe.
Thank you so much, Jemina. We have to move on. Thanks again for being here and sharing this very exciting work with us.
Thank you very much.
We will now have a longer break and continue at 4:45 Central European Summer Time with the podium discussion. I'd just like to remind everyone that we have our poster presentations going on in parallel to the symposium on Twitter. I'd like to encourage you to engage with the presenters there and to identify the posters that are of interest to you, and that you can then follow up with them tomorrow during the poster session in their respective Zoom rooms. I wish you a good break and look forward to seeing you later.
excited about everything. I'm definitely ready to get this going.
Just here to take it all in, you know, and just to be part of it.
What's up, guys? How y'all doing? So, yeah, the first few years were a little difficult, you know, just learning. Oh, med check? Oh, gotta go, guys. Gotta med check. So, yep, good luck, man.
I'm Dr. Traini. Nice to meet you.
Nice to meet you.
Welcome.
In the front and in the back.
They basically decide what to try.
To stand up is gratifying, you know, more than anything. It's one of those things that you're too excited to be scared. This was a massive event. You know, we had a sold-out stadium. We had, you know, people cheering, screaming, and yelling the whole time. It was beautiful, man, to see all this come together.
Welcome back. I hope you had a relaxing break and could recharge your batteries, because we have one last event for you to nicely conclude this first day of the Cybathlon Symposium 2020, our podium discussion, which was pre-recorded a few days ago. Our objective with this podium discussion was to bring together leading experts in the field with different backgrounds to reflect on clinical, technological, industrial, political, as well as ethical aspects and challenges of assistive technology. The topic of this panel discussion is promoting the provision and acceptance of assistive technologies, and it will be moderated by Miriam Dapp from the newly created Rehabilitation Engineering and Science Center in Zurich. Miriam, I pass the word to you. Enjoy the podium discussion.
Welcome to today's panel discussion. My name is Miriam Dapp. I am a communications and PR manager for the Rehabilitation Engineering and Science Center at ETH Zurich. I will be facilitating this afternoon's panel discussion. On the panel with us today is Professor Robert Riener, who is the founder and the visionary behind the Cybathlon. His research interests include human motion synthesis, biomechanics, virtual reality, human-machine interaction, and rehabilitation robotics. He is a professor for sensory motor systems at the Department of Health Sciences and Technology at ETH Zurich. Professor Armin Kurt is the director of the Spinal Cord Injury Center and the deputy medical director at the Balgrist University Hospital in Zurich. He is involved in technology-driven clinical trials and assesses patients that participate in the studies using spinal cord stimulation. Dr. Amit Goffer, founder and CTO of Up and Ride Robotics and Rewalk, is an inventor and entrepreneur. He is regarded as a pioneer of the exoskeleton industry. A wheelchair user himself, he developed Rewalk, the first commercially available exoskeleton in the US. Franziska Rieser is a member of the Swiss National Council, where she represents the political interests of the Green Party. Ms. Rieser is currently pursuing a PhD at the Rehabilitation Engineering Lab at ETH Zurich. Dr. Chapal Ghaznabis is a senior technical advisor for the WHO, where he works on promoting community-based rehabilitation and assistive devices. He also worked for other NGOs across African and Asian countries. Effie Vallena is a professor of bioethics at ETH Zurich. Advances in precision medicine and digital health generate ethical challenges for society. Effie Vallena and her team investigate those challenges and find solutions for health policy and practice. We are happy to discuss this very exciting topic with you this afternoon. I would like to start out with Robert Riener. Robert, please, can you tell us a little bit more about the vision of the Cybathlon and what you are hoping to achieve with this initiative?
Yes, the vision I originally had and still have is that we want to promote the development of useful technologies for people with disabilities. And by organizing the first event, I realized, or we as team realized quite soon, that there's a second vision, which is very important. That is that we want to also promote the process of inclusion. We want to produce an awareness about the needs and wishes of people with disabilities and try to better integrate them in the society.
Thank you so much, Robert. I'm just asking this question now into the round of our experts. What does the Cybathlon or similar initiatives, what does it represent to you? Should we start with Armin Kurt?
So as a clinician and dealing with patients, I do see the needs for accessibility of patients. Accessibility to the environment is a big demand. And also, as a second one, the participation in regular life, and professional life and personal life. And some of the devices that are spearheaded and developed are actually targeting these needs. So overall, this is really addressing a true need patients experience on a day-to-day basis.
Maybe we can just bring this on to Rapal. Speaking on the topic of accessibility, there's also a social demographic aspect to accessibility. Rapal, you have been working in developing and emerging countries, such as various countries in Asia and Africa. What are your experiences and thoughts on accessibility of assistive technologies?
You know, we want everybody everywhere to have access to high-quality assistive technology, irrespective of their socioeconomic condition or where they live. So people of the low middle-income countries has same rights as high-income countries to have a quality assistive technology so that they can be as productive as anyone else. And Convention on the Rights of Persons with Disabilities gives these rights guaranteed. So now is the time to make it possible.
I would just like to pass the word to Franziska Rieser, who is a member of the Swiss National Council, where she represents some of the political agendas of the Green Party, Environmentalist Party. Franziska, please share with us your thoughts or your experience, like what is the political situation currently like in Switzerland? You have been submitting a petition for facilitated access to assistive technologies. Can you elaborate a little bit on that, please?
Yeah, so welcome everyone, first of all. I think in Switzerland, at least, there is a broad consensus in politics, but also in society, that people with a disability, that they should be provided with some support, that they can gain independence, autonomy, and also remain or be integrated again in the labor market. Mm-hmm. Therefore, the social security system refunds and reimburses assistive devices. But so far, the social insurance, they only reimburse devices that are simple, that are economical and appropriate. Mm-hmm. And the problem, especially with new devices, is that they are normally higher in cost on the market, and therefore patients are not provided with these devices, although they would provide much better support for their individual lives. And we therefore requested to adapt the system, that not only devices that are simple and economical, but should be reimbursed, but devices that really support the individuals best. And the government in general, in principle, supported this idea and is now about to develop such a system to really reimburse also devices that are more expensive if the difference in cost corresponds to a real added value to the insured person.
May I just pass the word on to Amit Goffer. Amit, you are an entrepreneur and a visionary and the founder of Up and Right and Rewalk yourself. It's also, I understand, your solutions are very viable in a real-life environment, since you had the opportunity to test them yourself, but they are rather on the high end, like in terms of cost spectrum. So what are some ideas or some thoughts? How could those assistive technologies be made more accessible also in terms of cost for end users from a different economic background?
Well, as to the Rewalk, which is an exoskeleton that enables people to walk, including climbing stairs, and give really kind of a normal, say, life. This device is expensive. It doesn't have to be so, by the way. It can be further developed to be like high-end wheelchairs. The Up and Ride, this is a device, it's a wheelchair that can stand and sit, stand, recline, high sit and so, and you can go outside without the fear of tipping over, because it has automatic balancing situation. You're vertical on slopes. And the major goal here is that the person, the user, will be able to be at eye level, speak at eye level. Then the visibility of the disability is less obvious, diminishes actually. And it places the person more in the core of, it was mentioned here, core of society. It's very important for them.
I picked up the operative word being eye level, being on eye level, which also brings us to the topic of self-esteem, of dignity, of empowerment of people who are in wheelchairs or quadriplegic, or I think that's a very good word there to say on eye level and living a life on eye level with the rest of society. Before I dive into that topic though, I would like to ask Effie Vallena to share her thoughts and experiences on the topic of access again, because you are a professor of bioethics with your own chair and lab. What are some of the ethical questions that you are working on in your lab with regards to access?
I think, again, for the technologies that, the assistive technologies, I guess the priority is how to make sure that give people the opportunity to restore functions that that other healthy people have. So I think in that respect, the main question, the ethical question is, are we able to provide those to all people who need it? And that's a question, that a topic and an issue that was raised already, not only in low and middle income countries, but also amongst the wealthier countries. We do have differences in who can access what. And the problem will remain that as long as these technologies or devices come at a high cost, even in wealthier nations, it will be, again, less people who can access it. So I think one area of priority is how the technologies of that kind become more affordable. And I think that's where a lot of research can help with, in order to distribute them and make them accessible to more people.
I would like to pass on the word to Robert Riener, who, as we said, is a visionary, is somebody who thinks ahead and looks ahead and can imagine like a future beyond what we are currently, dealing with. So, Robert, you initiated the Cybathlon, which is competitive. It's competitive, it draws on performance, physical performance, but also mental resilience, I would say. If you want to compete in sports, you have to have some level of, mental resilience as well, which I think could be tied to Amit's approach of saying it empowers people with physical impairments if they can compete or not only be at eye level, but also be in a competitive environment and feel equal to other players in society. So between Robert and Amit, what are your thoughts on this?
I think the competition we have serves not only to bring the pilots, the people with disabilities, to the foreground. It's a much bigger chance which we have. The competition attracts many people to join, many teams to join the Cybathlon and promote their own developments. The deadlines we have makes them also to accelerate the developments and finish new pioneering work, and finally devices which may come to the market in an early way. Having many teams in a short time finishing development, we can push not only the market, we can we can flood maybe even the market in a way that devices are available, are accessible. And you need a large market, you need a large number of devices to finally also reduce the costs. And that's the side effect of this nice competition, which is nice to watch, which brings dignity to the pilots, as it should. The nice side effect is that we can really serve in the long run for accessibility and affordability.
Thank you, Robert. Amit, would you like to run with this topic?
Yes, I think that a major item is to emphasize that they, for the young people that got injured, say, spinal cord injury and so, that their life are not finished. And you can compete and you can be involved and part of active society. We should make an effort to enable the injured people to go back to the work force, work circle. This is what I see. And yeah, the new devices, they call smart devices, smart wheelchair, should be available, not very expensive, and society should kind of make an effort to bring those high-level devices to the individuals that don't have the ability for that.
Armin, you are highly specialized when it comes to spinal cord injuries. You are the head of the center at Balgrist University Hospital. What does your work imply in that regard? How can that be tied together in terms of having solutions that can be brought to market on a larger scale and therefore be more financially accessible?
I think they should be involved quite early. Patients do understand their condition better than you may think about. And they also are better positioned actually to explain you what may be able to do and what's not, and where the limitations are. And to understand what is the acceptance of patients in a given condition, in a given stage after injury, is also important to know if you can come with your elegant device and the patient is actually accepting it and you are actually targeting the needs the patient has. So having patients involved early in the process is probably very good. It's then with the researcher to understand where the judgment is appropriate and. But we do like to have them involved quite early.
Is that something that's already happening, or is that something that you would like to see more? And if it's not really happening so far, why not? What are the challenges to involving affected individuals earlier on in the engineering process?
I think we are here in the lucky condition that in the close collaboration with the engineers from ETH and the Balgrist Hospital, we are actually doing this by a day-to-day experience. And when we develop a novel device, whatever it is, the engineers are actually asking to get some opinion from the clinicians, but also at a very early stage to have some patients involved in piloting what the device is doing. And this helps during the process to readjust and refine what is needed.
I think it absolutely would also help with acceptance of the end users. Once they see, okay, they are being involved very early on, as you said, it's very customized to their actual requirements.
It helps very much for the patients and also for the therapists, which is a couple. They need to work jointly.
Amit, what are your experiences as the founder and CTO of both Up and Right and Rewalk, with involving the target users of those devices earlier on in the engineering process?
Yes, I must agree with what was said here. It is important, but I think that one of the problems is the early acceptance and the awareness of the both the disabled and physicians to a new device. This is kind of a chasm that you have to cross to make them. This is one thing, but to the point of the importance of getting, this is what we getting involved, the actually future users or the users, is very important to get feedback from them. I myself, I am quadriplegic, so, and I know a lot of people that do need wheelchair, all kind of illnesses. Spinal cord injury is one, multiple sclerosis, ALS, and so. So this was important. You talked minutes ago about augmented performance human being, make the person, a healthy person, more able. Well, this I would push and wait with that. Our goal is to help to return the people that are disabled back to society. And yeah, getting the feedbacks from them, this is one of our major part of our work. They're coming and piloting, trying the device, giving all kind of feedbacks, both for the functionality and the health, and so.
I would like to pass the word to Franziska. We were talking about the economic impact, and Amit said it is important to get people with movement impairment back into society. You know, they want to be empowered. They want to be productive members of society. That obviously also has like a economic aspect, which you could probably talk about sitting in the Swiss National Council. So people are productive, they work, they pay tax to be very blunt. So what are your thoughts and experiences on that?
Yeah, exactly. I mean, to empower the people with disabilities and to also afford to reimburse them assistive devices, it of course needs some money. But when we look, for example, to Switzerland, we speak about 1% of the budget of the social insurance that is spent for example, prostheses and assistive devices. So we are not in a range where we speak about millions and billions of dollars or Swiss francs. And I think for a society as a whole, it is of much interest to spend this money to really give the opportunity to people to bring them back into society. Not only that to empower themselves and that they have the chance to get back to labor market, but also for their social aspects, because to be more happy, to be if you can work again, if you get really included into society, into the labor market. So I think for a society as a whole, it is definitely an area where it is worth spending the money.
Absolutely. Which brings me to Effie. I think that's exactly the point. I mean, it does not only benefit affected individuals. I'm not sure if everyone in this round agrees. It benefits society. So to me, that's sort of like an ethical question. Do we want to, as the many, do something for the few, or is it not the other way around? What are your thoughts on this, Effie?
Well, I think that we all have, first of all, even if things cost money, right, in healthcare, not only devices, everything. And so we do have an agreement that we live in a solidarious kind of system, that we support each other when we have needs. And the same principle applies here. Again, it is a priority to make these devices and these technologies as affordable as possible, and I think that's a common interest and a goal. But I think it's really important to make sure that we all contribute in order to make sure that all of us have at least a fair chance in living a life where we can pursue our goals according to our potential. So the same applies here. And for example, one other aspect that I find very interesting, and from the ethical point of view it is important, is these people with disabilities, in that sense, that are excluded from many aspects of social life, many aspects perhaps also of the of productivity and labor life, and making a contribution to including them is not just a benefit to them, it's not just a benefit of financial nature because they will pay more taxes or whatever. It is also a benefit for our society as a whole. The fact that we look after each other and we include helps our societies become better societies. And I think that is another kind of perhaps long-term and you could call it more high-level sort of outcome. However, I think it is also crucial for the kinds of societies we want to live in now, and looking after those who have needs.
Beautifully put, Effie. Gopal, I would like to pass the word on to you because you have a lot of experience as a senior technical advisor for the World Health Organization, obviously in developing and emerging countries. So if you pick up from where Effie left it off, so how do you see this, and what can be done to sort of shift perception of society towards, it's not society that is doing people with movement impairments a favor, it's more like about inclusion and being a community. What are your thoughts and experiences on this?
I agree with all whatever have been said so far, but issue is also I see it in a different way. By not doing what we are losing. We talk about reimbursing one product for a person to become productive. But if we don't give that product, we are not making only that person effective. Even we are making the family ineffective, the caregiver, the immediate person. We know many people, the husband or wife cannot go to the job because husband or wife do not have a wheelchair. So other takes care of another person. So it's a double loss by not doing. And that's what we are trying to make people understand, that by providing is a smart investment, because it's the person as the immediate family members, caregiver, partners, they all become productive. But by not doing, we create more harm to the economics. So the policymakers has to see it from the other direction rather than just seeing the cost of a product. Absolutely. And the cost of a product is very relevant term, because what is expensive today, I'm sure it can become affordable tomorrow, provided we increase the number and work on the economy of scale. During this COVID, we have seen there is not much difference between low middle income countries and high income countries in terms of access and provision of assistive devices, to be honest with you. And it showed a lot of loopholes even in what exists even in these high income countries. So we completely believe that solution is not only in Switzerland, not in Western Europe. Solution is not global. So we have to see that how we can increase the global market so the product price comes cheaper. And then only everybody can afford and nobody will grumble to reimburse these products. The problem is that at present, the current market is very small, very exclusive, and the products are overpriced.
Franziska, what do you think it takes to make the case for better financing of assistive technologies in the Swiss Parliament? So what do you think it takes? What can convince them?
So I think maybe in contrast to what we have heard about the global level, so in Switzerland, as I mentioned in the beginning, we have a consensus that we need to support these people and to also provide them with assistive technology. I see at the moment more the difficulty in how we can provide them with also like novel technology devices that are developed and built with new technologies that are not tested yet for years and that normally also are more expensive. Because to convince the first of all, the politicians, the policymakers, but also the social insurances, one needs to really see the added value for the people and for the persons themselves. And I feel, I mean, here at this symposium that Cybathlon itself is a great opportunity, especially for policymakers to see what assistive devices in general, but also novel technology can provide and can help these people, and also maybe to see what cannot be achieved with these recent technologies yet. And so one can really see with your own eyes that the benefits that people have when they, for example, with a actuated prosthesis can cut a piece of bread by themselves again. So it's visual, and this, I think, is a way to also convince and show people that are maybe not themselves in the technological area that these devices are really needed and provide a better quality of life to the individuals.
Thank you, Franziska. I think that is really a good point. Robert Riener, do you see the Cybathlon as a showcase for novel technologies if we want to maybe now look into the future, 10, 15 years, more, let's say, sci-fi, novel technologies, the Cybathlon and similar initiatives, can it be a showcase in order to make the case with policymakers?
Of course, we want also to entertain the people, but the main goal is to show, and that has been said, what technology is available and what is not available. There's too much hope of people in our society who are not working in research. They believe that we have already all technical solutions, or the military can do everything, and the researchers have great ideas in their drawers, and they don't show it. And we have to show that we are not as advanced as many people think. And that's some kind of clarification. We have to clarify the society. Otherwise, they are getting maybe afraid about too fancy technology, which might be used not only to augment, but also to enhance healthy people or people without disabilities. It's very important to show what can we do nowadays. We can't do too much. We have to do more. We have to spend efforts and also money to improve the technologies and to improve the integration of technologies to that circle of people who might benefit from it, and we have to invest efforts into society to communicate finally.
Thank you, Robert. This is a question I would like to just put out there in the room. What sort of ethical challenges would arise if we were to have like AI that's sort of like overtaking human, computing capacities or movement capacities? So, yeah, in a distant future. I would like to start with Amit.
Today, you can hear and see researchers that install a chip in the human brain, but and a lot of research about this, and I believe in it in order to solve difficult illnesses. I believe in in illnesses like Parkinson. I'm PhD. I'm not an MD. But there you can combine technology with the human brain. Right now, it might be a bit difficult to help people that are disabled to involving AI in the devices. Right now, there is a place for the future. Yeah.
Thank you so much. Armin, if you would like to build on Amit's thoughts, you work in spinal cord injuries and you are a medical doctor. So what are your thoughts on AI and possibly implanting chips and your thoughts?
So I'm not at all concerned about AI, rather about the people who apply it. AI is a technology, and if you have a concrete and a clear question, AI might be a tool to help you. So the considerations that AI is overtaking your thoughts and whatever is not the case, at least yet. So I think AI is a hopefully strong tool to help in some of the decision makings that machines do need to know how to best help the patients. And so if AI is better doing this than other rulers and whatever, that's fine. So I'm not concerned about the AI itself. It's always about who is applying it, what for.
Effie, what are your concerns on AI being used?
Well, I think, as Armin and others said, I think today what we're seeing with AI is a technology that solves some fairly simple problems, and there is, of course, a lot of sensationalism around what it could possibly do one day, and it could overtake our intelligence, etc. I'm also not seeing this happening anytime soon. But I think the fundamental question in here is whether we want something like this to happen or not, and therefore whether we want to work towards allowing and letting any technology, in particular here AI, become that. Is it in our interest to have a technology that becomes much more intelligent than us? We have had technologies that become better than us in many ways. So we have technologies that run faster than us, that lift heavier weights than we do, etc., etc. But do we want it? All of these technologies we control. Do we want to have any technology of which we stop having control over? And the fundamental issue there is essentially, do we want to lose our own agency and autonomy? And then, of course, if that's the case, are we allowing all sorts of manipulation to be made in the technology and the lives we're living? So I think, again, I agree with Armin. The question is, who develops the technology, who uses the technology, and then what is the purpose of all of that? The purpose in a specific case, but also the purpose in general. What kind of society we want to have? One that we individually have control over our actions and of what's happening, or one where we cede control. And once we cede control, the question is to whom?
Thank you so much, Effie. Robert?
Thank you. I fully agree with what Effie and also Armin have said. From my point of view, it's about developing useful technology which is user-oriented. We have to speak to those people who needs any kind of technology. It must be user-oriented and driven. It does not make sense to develop something just for fun. I disagree, for example, with the work from Elon Musk when he's sending rockets to the Mars, trying to solve any problem on the Mars and ignoring the problems we have on Earth. I think we should focus on the problems we have here and go then step by step to solve it. And then I think, and then we have the right people who do not do crime with our technology, then I'm optimistic.
Thank you so much, Robert. Over to you, Rapal. Who has access, and if people from highly developed nations have access to AI, what happens then to developing country end users? Will they then fall back even further?
I think to put all AI in one bracket is not a fair. AI is too broad, and its applications also too broad. It depends which AI we use for what purpose. So I don't see the world exactly like a developing versus developed countries, because there are many rich people exist. I have been told that one European company sold most intelligent advanced prostheses more in India than in UK. So there are rich people everywhere, and there are takers for everything everywhere, somebody. So these are the opportunities for now and the future. And I think it's better we control it rather than we are being controlled by the technology AI. So it has a huge possibilities, and we are adopting it. And in WHO, we are working on the group of experts to take advantage of AI to guide the primary health workers in the developing countries to select, to support the users and the providers in decision making. So there are many applications of AI. And I also think what is expensive today, it will not be expensive forever. So, there are more mobile phones in the developing world than the developed world. So things are changing, and this technology is changing things very rapidly. So now the issue is whether we want to be part of this change or we just sit outside and see the change. Because technology will advance and advance because there are a lot of reasons and interest behind. So it's better we control the technology than technology controlling us.
Over to Franziska, from a policy point of view, like Swiss policy point of view, what are your thoughts on AI and where it's going or where it might go in the future?
Yeah, I think we still face enough challenges in formulating the rules and the regulations and the laws regarding the technology that we develop at the moment. And I think, as Robert Rino mentioned, we shouldn't, also from a legal point of view, shouldn't tackle the problems that might arise maybe in 20 or 30 years, but we should focus on the problems and the challenges we have right now. And nowadays, for example, we already have drones in commercial areas that are used and still lack the proper regulations for these kind of technologies. And I think this is where we first have to start. And in case that AI at some point will go above and beyond these regulations, then we have the time, or it is the time then, to again discuss and find the solutions for that situation.
Robert Riener, how do you think the Cybathlon can support the cause of a wider acceptance of assistive technologies, taking on board some of the discussions we had this afternoon?
With the Cybathlon, we exactly try to address this problem, that we want to develop and provide developments or promote developments that are useful and that are patient or oriented on people with disabilities. And that's why we have in our boards people with disabilities. That's why we are in contact with many stakeholders, with physicians, with architects who are experts about barrier-free environments. And we try to take into account the challenge and the problems which we have nowadays, and then together with the pilots are working on it. We also serve or take into account that the tracks we are designing for the races, they are based on, not all of them, but most of them on challenges of daily life. And so that the development of these devices is going into the right direction. We we take into account that the pilots are getting in contact with the developers in a very early stage by helping the communication between the engineers and the physicians and the people with disabilities.
Thank you so much, Robert. Our panel discussion is drawing to an end. I would just like to give every panelist the opportunity for some closing remarks. Amit, thank you so much for your time. Any closing remarks that you would like to share with us this afternoon?
Well, to the Cybathlon maybe will contribute to encourage the disabled to try new things. This is a problem that not sometimes the people are very comfortable in their own old wheelchair. It's difficult to take them out of that.
Thank you so much. I think it's beautifully put. It's about mindset, you know, and really encouraging people with movement impairments to also empower themselves and really go for it. I think that's beautifully put. Thank you so much, Amit, for joining us this afternoon. Armin Kurt, what are your closing remarks? What did you take away of this afternoon?
Yeah, I think I would like to encourage Robert and his team to come up with the most fantastic device, which is really making a difference. At the first level, don't look to the price. The price is always a weight against what it delivers in addition. So make the most glorious and most effective device, and then we'll handle down the prices.
Value over price. Rapal, what are your thoughts?
No, keep it up, keep on going. We have to look at more also in future from high-end technology to high-impact technology, and think global, because solution is with the global population, and that only can make even the cost becomes affordable, even in this part of the world.
Thank you so much for your time and for your valuable contribution this afternoon, Rapal. Appreciate it. Effie Vallena.
Perhaps, again, one more aspect of the Cybathlon that I think is really important is the fact that it gives visibility to an issue that maybe societally we think it just affects a few people and not all of us. And so the way it's presented, what's happening there, I think it reminds us that this is an issue that we all, that affects us in some way, and we can accept and contribute it and support solutions.
Thank you so much, Effie, for sharing your thoughts with us this afternoon on the very important topic of ethics. Appreciate it. Franziska Rieser, you are sitting at the policymakers' table. What are your closing remarks?
Yeah, I think the Cybathlon showed that it is a really great opportunity to bring together the people that develop the technologies with the pilots, the users that use the devices and the technology in the end. But doing this in a public space and bringing it really into a public awareness also brings policymakers as maybe a third party into this event. And I think this is really one of the big contributions that the Cybathlon brings, that it brings technology to the society and shows what is possible today and where we have to go into the future.
Absolutely. Thank you so much for joining us this afternoon, Franziska. Robert Riener, would you like to sort of like tie it up and tell us where we're going with this year's Cybathlon?
Yes, the next Cybathlon will take place in November as a virtual event with many teams and many hubs. We increased from one hub in Zurich to about 40 hubs all over the world. We developed the Cybathlon out of a need to improve the function of the devices, make them useful for the people with disabilities, and to foster, to improve inclusion. Now, Cybathlon is growing, it's getting bigger and bigger, that's great. And now I say something which might sound dangerous or strange. My hope in the long run is that we do not need anymore the Cybathlon, because we might have solved these challenges and these needs we have, because we might have very good technologies, maybe combined with biological technology, biological approaches that can limit the sensory motor impairments of people with disabilities or avoid them, or improve also the view of the society on that problem. It's also a lot of things referring to attitude of people, how they see people with disabilities or not, that we might have an included society, and then we don't need anymore the Cybathlon.
Thank you so much for those closing remarks. Thank you to all the panelists who joined us this afternoon. We appreciate you and your work very much. and we are looking forward to Cybathlon 2020. Thank you so much.
Thank you.
A big thank you to all the panelists and to Miriam for this interesting discussion and for sharing your thoughts on these important topics. This brings our first day of the Cybathlon Symposium to a close, and I hope that you enjoyed all the inspiring talks, posters, and discussions today as much as I did. We'd like to thank all of you for actively contributing throughout the day, for your availability and flexibility that was required to put, or is required to put such a virtual event together. I would also at this point already like to give a thank you to all the people that are sitting in front of me here, pulling levers, making sure this all works and making sure we don't panic when anything unexpected happens. And especially I would also like to already thank the colleagues doing the closed captions and our colleagues in the other room doing the live sign language translation. I think we've given them a lot to digest today. Tomorrow, we will continue with the 3 remaining Cybathlon disciplines, namely the arm and leg prosthetics and the brain-computer interfaces. Depending on where you are, we wish you a good night, a good evening, or a great afternoon, and we look forward to seeing you again tomorrow.